প্ৰথমতে লেপটপ ইউজ check. So there is one mic open. John. Yes. Check. So can we start the feed now? Maybe just 2 minutes. Huh? Get the folder that the zip folder that we have shared yesterday in the chat.
Okay. So very good morning to you. I think two eventful days for you all. Very different topics. So today we come to the another topic, which is basically on classifiers. And this is not going to be a very technically illuminating probably talk, but it is an overall idea to give you an overview of what we are actually doing in terms of the machine learning, in terms of machine learning in this particular course, which you will be actually practically start doing from this afternoon and until the end of the course now. I'm going to give you an overview of classifiers. And specifically, I'll talk about actually one of the particular classifiers that we are usually using in our own work, and one which you will do some experience using this afternoon in the tutorial. We have shared you on your WhatsApp. We have shared you a zip file, and we expect that by now you must have downloaded it and unzipped it and wait for our further instructions on that. As we start the afternoon session, we'll talk about it. So basically today, this morning, I'm going to touch upon three topics. One is a very short introduction, very basic introduction to classifiers. Then I'm going to talk about the type classifiers. Finally, I'm going to talk about the classifier that we use in our work most of the times, which is the QDA classifier, quadratic discriminant analysis, which we'll talk about and work on that in the second half of today's tutorial. Also, finally, I'll give you one example of how we are using classifiers in our works to get some of the linguistic hypothesis tested in some languages. So if you remember on the first day when I was talking to you about different works, what are the works that are done using different sorts of levels of machine learning. I talked to you about this work on rhythm, and I showed you this particular slide where, if you remember, I showed you that with the rhythm characteristics and some other temporal measurements, we tried to predict. We tried to see how much we will be able to predict the region the person comes from based on the rhythm that they produce or other temporal measures that they produce. So we had some of those measurements such as syllable per segment per second, syllable per second, and then these are the standard measurements that are used to capture rhythm. So I gave you a slide where I showed you that, if you have more percentage V, it will go towards one of the rhythm classes. If it is more NPVIV, then it will go to another class of rhythm measurements, if you remember. If you don't remember about it, don't worry about it. I can just quickly go over this one. So what we did is that in the example that I gave you on day one, what we did is that we collected the speech data from Assamese speakers reading North Wind and the Sun in Assamese, right? And then what we did is that we basically segmented all their consonants and vowels, and we tried to measure what kind of rhythm Assamese speakers have. And then if you remember that one particular graph that I have provided you on in lecture 1, in that graph we saw that Assamese basically clubs together with Japanese and some of the Mora-timed languages, not with English, not with Spanish, which are stress-timed and syllable-timed languages. Then what we had in that database is that we had the data from 5 different regions of Assam, 5 different towns of Assam actually, and we tried to see if we can discriminate, if we can classify those towns automatically or not. So this is what I have told you that other day, that the 3 dialect areas which these 5 towns belong to, the 3 dialect areas being Eastern Assam, Central Assam and Western Assam, we could successfully classify them automatically with an accuracy of about 47.4%, right? And the 5 regions together, when we tried to find out where the speech comes from, in that case we could actually discriminate with an accuracy of about 43%. That is what our conclusion was at that point of time. So here we have shown that what happens when we are actually using the system, the classifier that we were using to predict which region a speech comes from. If we give only one feature, which is segments per second, this is the accuracy that we get for one of the 5 towns. For predicting one of the 5 towns, it is about 24%. If it is like one of the 3 dialect areas, like Eastern, Western or Central, it is about 40%. However, as we add more and more features, if you can see, here are the single features. Here I'm adding like segment per second plus syllable per second, should have been syllable per second, and then it goes a little bit higher than the previous one. But if we add the other features, which are the rhythm features like percentage V, delta V, Varco V, etc., then it jumps up to a higher accuracy and goes up all the way to about 42.1% of accuracy of predicting the correct town, one of the 5 towns, when we add all the features together. Similarly, when we are looking into dialect areas, one of the 3 dialects, which of the dialect areas does it belong to, that prediction has an accuracy of about 47.2%. Now there are like other things happening. For example, if you take off one of them, the accuracy increases. If you take one out of this one, the accuracy in the dialect idea, etc., increases. What I wanted to understand from here is that I wrote something like the 5 dialects, 5 regions are discriminated, right? And when I'm talking about these 5 regions were discriminated with an accuracy of 42.8%, this discrimination was done automatically. The machine basically did it. So we provided an unlabeled data to the machine and asked it, so with the data that you have got so far, can you predict what is the dialect this speech belongs to? And then it could do it 42.8, almost 43 times out of 100 times, it could do it correctly. So we provided data to the system from 5 different regions, which were the Tinsukia, Jorhat, Nagaon, Borpeta and Nalbari. They come from when I'm writing this, I'm actually writing from east to west. So you can probably visualize in your mind. So the middle one is actually in the middle and the last 2 are in the western part of Assam. So we provided, as I said, all the rhythm measures, all the rhythm values, percentage V, Varco V, etc. For each sentence produced by each speaker with their regions indicated. So what we did basically is that when we got the north wind and the sun, we chopped each breath group actually, wherever the person stops, starts breathing, that is where we stopped it. For example, you can say something like Uttara Batahar Belir Mazat, there may be somebody may start breathing. So we consider that as a break and we mark it there, and we take only the portion between one breath to the other breath. So we take a breath group, right? Another criteria we followed while doing that is that actually if you have very short breath groups, these kind of measurements are not effective. So we made sure that we take at least 7 syllables in each breath group. So the minimum number of syllables in a breath group should be 7. And why 7? Well, there are people who have done research before and they have shown that until 7 syllables, it is not probably a good measurement. From 7 syllable onwards, it becomes a much more reliable measurement. That's why we take 7 syllables per breath group. So we used that kind of data and then we extracted all these different measurements. How we got the different measurements? Some of the measurements are very easy, as I have told you the other day. Percentage V, basically it is the how much of the total speech has vowels, right? But if we go on to NPVI and like some Varco V etc. measurements, then we are going to a bit more complicated when we are looking at one duration in relation to the following duration and so on and so forth, right? So that is kind of complicated. If you are interested in knowing more about these measurements, of course we can talk in the break, and also I can suggest you some readings, but at this point of time, knowing about these measurements is not our goal. Nevertheless, when we collected the data, and when we basically extracted all the measurements, so the spreadsheet on which we have collected the data would look something like this. On the first column, you can probably see regions are written. So Jorhat, Nalbari, Jorhat, Nalbari, Barpeta, Jorhat, Nagaon, Tinsukia, etc. All these 5 regions are there, right? We have actually collected all the data, and we have got all the measurements together and put it on the sheet, right? Then we have the speaker information such as JF02, JF03, etc., etc. Then we have gender marked there, again from the second character of the file name, of the speaker name. Actually, you can already guess what the gender is gonna be here. So we have given FF, MM, etc. And here are the measurements of the different measurements, such as percentage V, delta V, which is the standard deviation of the vowel duration, Varco V, SDC, etc., etc. Right? So we have got our spreadsheet or our raw data, right, arranged like this to be processed in the following steps. Now, now let's assume what we asked the machine to do is that we provided a new data to the machine, somewhat like this, what you can see on the screen now in the red letters, and we asked, can you guess where it is from? Right. Now I want you to take 1 minute, maybe 1.5 minutes, and see if you can predict actually which region this data is from. Can you give feed to the screen, please? Yeah, thank you. Bingo. So some people have said Nalbari. Absolutely right. How did you do that? You went on, looked at the pattern of data, then try to match it, and that is exactly what the machine is doing. Right? What you have done is exactly what the machine is doing, just that as a human being I don't have to tell you how to do it. The machine, I'll have to tell it how to do it. Right? But I'm really greatly pleasantly surprised that more than one person got it right. I thought that nobody would get it right. Okay, so now in this data, when we have these kind of data formats, we have to understand some of the basics of how this data is arranged. So this is basically the top part where we have written each column name is basically the header, right? It may be basic for many people, but I'm just telling you that. Now, we have different variables here. For example, speaker itself is a variable, gender can be a variable, then percentage V is a variable, then all these are different variables that we have in the data, right? And lastly, what we have is that these are different classes, right? So what you have just done when I asked you where this data belongs to, you basically classified the red data into one of the classes, right? And that is basically that is all what classification is, right? So our job is basically to look into how many classes are here. Here there are 5 classes, which is named as region in this database, right? And this database, the 5 classes are basically Tinsukia, Jorhat, Nagaon, Nalbari, Borpeta. Again, I'm repeating that I'm starting from east to west. And the labels are Tinsukia, Jorhat, Nagaon, Nalbari, Borpeta, as you can see here, right? Today we are going to actually, in the second half, we're going to take this data and we are going to perform a few operations, a few classifications, and show you how it is done. Okay. So our objective, right, in a classification, right, in the objective of a classifier as such, right, is to train an algorithm, what you have trained in your mind just now, to train the machine with an algorithm which can predict what the label for the column, the row X will be. Okay. So this is basically what your classifier basically does. So what is the work process of a classifier? Well, you give the data to the classifier, right? So I hope I'm okay with you're probably getting what a classifier is, right? Classifier is nothing but an algorithm which takes raw data, right, without any label, and then provides it a label, right? So what is needed for that? So we first need to train it, right? What I did with you just a little bit, some moments ago, what I did is that I gave you some labels there, and I asked you to think where this data must have come from, the unlabeled data must have come from, right? I trained you, right? That is what we need to do. So for training, we provide raw data with labels. Okay, we provide raw data with labels, and then we build a model, what you just made in your mind, right? And after some time, if you have looked at that data for a long time, you don't have to go and match every time. Actually, just looking at the data, you already have an idea where this data would fit into in the table, right? Just like what happens in speech, right? Every day when you hear speech of different types too, you don't have to go and match everything every time with all the characteristics, right? You already have the model, you just fit in there and see what it means. So we have to build the model, and then comes the testing part, or this is the training part, and then comes the testing part, or the real usage part, where we are using this model with some data with no label. We are going to feed the data with no label, and there would be some sort of predictor here, there can be many different types of predictors, right, based on some sort of statistical prediction, and then it will assign a label. So this is what basically a classifier does, and as I told you, this is a very basic basic lecture on classifiers, because those who are from the technical background, you must have already known all about the supervised, unsupervised, and semi-supervised classifiers, but it is mostly for our linguist friends, so that it is easy for us to go to the next step. Now the question is that that I just gave you some data with the numbers. It is difficult to know what the characteristics are until I give the label. Is it always necessary to get a label? Look at this data, right? Can you predict, can you guess how many classes are there? 3 classes, right? And then can you if I ask you that, can you draw a boundary around, can you cluster them together? Can you do that? You'll be able to do that, right? You'll cluster it here, second cluster here, third cluster here, etc. Right? In that case, you're not using any prior knowledge. Actually, I'm not feeding you with any labels, right? Without any labels, you are able to now actually classify the data or put labels to the data, right? And like that, some of the classifiers actually don't need any labels. They are called they are basically unsupervised, right? They well, basically, like, classifiers that use unsupervised learning. So to summarize, basically, like, if we want to know about classifiers, the basic idea is that it is basically an algorithm to assign class label to some sort of data that is being input, that is being provided, and it is usually trained using labeled data. Sometimes there are no labels, as we have seen in the last case. Sometimes some of the data are labels, but many are not labeled, so it's a combination of the two, right? And in case of testing, what happens is that it receives unlabeled data and outputs the different classification labels. Okay. Any questions at this time? Yeah.
So the data that you showed us from the chart, that when you, yeah, here.
Can you use the mic?
I don't think this actually works. Do I keep putting it then?
Okay, I think this is on. No, this is not on.
Okay. So in the previous chart, when you showed us that it's right in that chart, there were labels, but there were colors.
Yeah, I got it. I got your point. So, sorry, I got your point. Let me find a. Maybe this one will work. Yeah. So I got your point.
Yeah. So wouldn't the colors be a type of label?
To some extent, true, but you can think about it, like, as if we don't have, if the machine does not have any idea about that, process the colors. That is for your convenience, right? Then even then, only from clustering, if there are three groups of people working in different places, you will be able to get it done. Check. Is this on? Sorry? Okay, okay. So they're in complementary distribution. Okay.
What was the size of the data when you were training it?
Very small. It was about 855 rows.
855?
Yeah.
So how did it work really? Because in unsupervised?
It is like, it is, no, not unsupervised. We used, this one is supervised.
Okay, so SVM?
No. This one was QDA.
Okay.
Much low level, that's why we used QDA.
No, but that works well on small data.
Yeah, works well on small data.
That's what I had a doubt on.
It's like 855, if I remember it.
Because we
Jashi, was it 855, was it? I was off by 6. Yeah. Fine. And that too, actually, like, today the data that you'll see is 849, but then Lina is also sitting here, so Lina would know it even better. So then we removed some of them again because they were less than 7 syllables. Today you will see some data that will come with actually less than 7 syllables also, but we are keeping that there. I cannot recall that paper we said, how many I don't remember. Yeah. Anyway, so yeah, QDA is very good for that. That's why, that's the last bullet point of the slide actually, that why we are using QDA. Okay. So I gave it out already. So these classifiers perform a lot of different tasks. One of the interesting thing that I was doing yesterday, I was looking for something on Google Translate, and as soon as I typed in another language, it automatically goes and detects it. Right? Imagine the number of classes it might have. Right? There are 200 languages there, but it immediately caught that you are writing in Assamese, so it changed the screen. Right? So and then you get much more interesting and much more complicated things like this. That different types of dogs. I always give this example of different types of dogs because the dogs are the most varied, I think, in terms of size and shape and everything. You can have a dog this big and then have a dog probably bigger than a cow or something, right? So it's very difficult to classify them, actually, to identify them. And then if you have a cat here, so the main task of a classifier is to sort the cat out of the dogs. So, and also, while doing that, it has to find some features. Fur does not work. Ears don't work. Right? There has to be some unique features finally which would work in classifying the dog class from the cat class. This will come back again. So as I said, some of these classifiers are basically supervised, right? And some are unsupervised. And then some are basically semi-supervised classifiers. And then many of you have already come to know why they are called unsupervised, supervised, or semi-supervised because of these reasons. For all the training data, in case of supervised, the classes are provided. So we have to provide the classes. So it has basically two information there. Exactly the class label it has, and also how many number of classes are there. So it becomes much more easier for it to classify the data. So in unsupervised, for all training data, classes are basically not provided, right? And then if it's a semi-supervised, or there are many other names also for that, some amount of training data is maybe labeled. Many of the data may not have any labels in them, actually. So when we talk about supervised classifiers, then there are quite a few classifiers which will fall under this category. Remember also that some of these classifiers can be run also as supervised or unsupervised also. Not all of them, but some of them can be. But we are not going into that. So one is the supervised classifiers and support vector machines, SVM, the very common ones. Linear regression, very basic ones. Logistic regression. Then random forest, where you have you make basically decision trees and different types of decision trees with different variables, and try to get the best score averaged out of all the decision trees to make a judgment on what the predicted class should be. Then one of the more advanced one, but yet very how do I say, very which can deal with very simple data, is something like linear discriminant analysis. So basically it can only discriminate between two classes which are kind of well separated and which do not have much overlapping boundaries. If it is more complex data, it cannot work very well. But the better than that is our own the quadratic discriminant analysis, because quadratic discriminant analysis is some sort of very flexible classifier, and I'll show you why it is a flexible classifier in a little bit from now. So these are the supervised classifiers which are used for classifying data, right? And as I have shown you that we are using quadratic discriminant analysis in many of our works to classify categories in speech data. So it works pretty well in speech data compared to considering its complexity the speech data has. So you have, we also have the unsupervised methods such as k-means clustering. So it basically, like, given a random set of data, then it finds the best cluster, like what you have done just now, right? And provides clusters. Then principal component analysis, Juraj has already talked about it on day 1, I guess, right? And it also is also dimension reduction. It performs dimension reduction also. So what it does is that if there are, like, let's say all those variables that you saw from V1 to V9, some of the variables, if they are not very useful, it will actually indicate which ones are very useful and which ones are not very useful. So it will find out the principal components in the data itself. So GANs, like, many of you have probably used generative adversarial networks already. And then one of the words that you must have heard about in this particular course so far is something like an autoencoder. And autoencoder is, again, if you are not sure what each of these mean, you don't have to worry about it, right? You can always, like, there is enough time to go and understand about each, but I don't think, like, even, like, very experienced scholars would be able to will be experts in all of this at the same time. So anyway, so this is about autoencoders now. You must have heard the word autoencoder from Juraj already. So basically these are, again, neural networks. He has also mentioned what neural networks are, right? It creates, it uses networks and then encodes the inputs into smaller representations. So basically, again, just like PCA, it just like, dimension reduction, and it finally contains only the important information that is there. How it finds the important information is very interesting, because it goes back and forth, tries to see, like, whether that information is enough to classify this, because I already know the labels there, right? It goes and checks, okay, if I take only this information, would it work back? No. Okay, I'll go and get one more, or like add or delete one more information or one more feature. So it goes back and forth and runs and understands what the best information to represent the data will be, right? So finally it gets, like, only the important information that is enough to have this the data represent correctly. A little later, I will also, maybe now, maybe not now, in the second second lecture, I will show you that we can do it with different kind of things. For example, vowel data, right? Vowel data is a very, like, temporarily long data, right? I mean, a vowel can go for 100 milliseconds or something, and we can, like, start calculating vowels in, like, 100 different places in those 100 milliseconds. However, what we can also do is that we can actually make a summary of that, whatever is happening in 100 milliseconds, and give only one feature for each vowel, which actually captures the property of vowel very well, or tone, or any of the linguistic features, and then which is easier for us to work with, like, classifiers like this, which we feed again as features in the classifiers. So these are basically, like, the small, it basically what it does is that it goes back and forth and finds out which smaller representation is the best, which can best represent the input data. And these smaller representations that I'm talking about, these are basically called the latent spaces, right? Which is one word that Juraj has been using, I think, at least once, twice, or thrice so far, right? So these are called, basically, smaller representations are called latent spaces that we use to probably give property, or, like, provide characteristics to some sort of speech data, or some from some dialect data, etc. So again, so if you look into like any kind of classifier or any kind of neural network tutorial, then you will see pictures like this, because as I said, this cat and dog, there are two things that are happening. Like, it is a complex problem, number one. Secondly, on internet there are lots of dogs and cat pictures that are available for free. Like, everybody posts a cat and dog picture once in at least in their life. So like, we have a lot of these data and they keep on appearing. So if you look into this cats and dogs data, then what is happening is that we can see that each of them have different height and tail length, etc. Right? And if you consider like, the cat class and the dog class, right, maybe you'll be able to get the most important information from its height and the tail length, right? And that is probably serve as your variables, the important variables that are using to classify the dog class and the cat class. So the important point is that, like, to find out what works, like, in the best in classifying and in your classification, that you can go by intuition, number one, and the other way is to by experimentation, like what the autoencoders do, go back and forth and find out what works. And I'll give you one example of that in the second lecture today. Also, how we find out what are the most important variables in certain classification algorithms. So basically what QDA does is that the quadratic discriminant analysis, which is the last one that we have talked about earlier here, right? And that's why I have put it in bold, because I'm going to talk more about it. And this is the one that I'm most comfortable with and I use most. So I'm going to talk about this more. So the QDA, quadratic discriminant analysis, what it basically tries to do is that tries to see how this height and tail length, how this data or how the numerical data of this height and tail length are spread for each category. It tries to see, like, in a space how the numerical representations are spread for each category, just like what you have seen in the earlier, the red, blue, and the green dots or something. It also tries to see how the values of height and, let's say, height and tail length is just an example, right? It could be many other things, right? It also tries to see how these values basically co-vary with the two classes, the dog and the cat classes, and it tries to see that if dog becomes dog class, then the numbers change. If it becomes cat class, then it becomes the numbers again change, etc. And based on this, like in the space where all this data is distributed, it draws certain boundaries for each class, right? So once it, like, it draws the boundaries, then it basically assumes that anything that comes on the right side of the boundary is going to be a cat. Anything on the left side of the boundary, it is going to be a dog, right? So this is all about, like, making a boundary boundary in the space, a distributed space for each of the classes, right? Like what we have seen in the earlier case, remember? The red dots and the green dots, etc. There, like, we can have, like, if it falls into that red category, we know that it's going to be a red dot, right? However, the point is that it is not always the case that everything falls into the right category all the time, and that is why we have an accuracy of 42.8% in some cases, because some data are actually misclassified into another category, right? And that is common. So in order to make it into, like, into that like correct category, you probably need a better algorithm and a lot of data. Probably it would happen. And when we are doing in the second half, we are doing a problem. Yeah, we are doing a problem of our own QDA classification, right? Which we are going to try. In that, we will see how the number of classes actually affect your accuracy, right? And there are many other things, of course, like that affect the accuracy, which I'm going to talk again. So like now what happens is that the boundaries can be taught in many different ways, right? The boundaries, you can go ahead and draw a strict boundary, right? Which what linear discriminant analysis does. When LDA draws a boundary between two classes, it's a strict boundary, and which is going to be a linear boundary, which is going to be a strict boundary, right? However, if your algorithm is powerful, if your algorithm is advanced, then the boundaries would have a lot of flexibility, right? So for example, QDA can go a little bit flexible. Actually, it can bend a little bit and then encompass all the the data that goes a little bit away from the exact prototypical classes too. I'll give you an example of that in the following slide, so don't worry about it. So in case of QDA, in case of this, QDA works better because speech is that kind of data, because how complicated speech is. Within the same speech, you might be actually going into from one space to the other. So when it makes the boundaries, it takes into consideration those variations. It may be able to take into consideration those variations and put it inside the boundaries, right? It will be probably clearer if we go a little bit forward to the next few slides. So theoretically, what you need to understand is that QDA is basically a kind of flexible kind of classifier, right? It does not draw linear boundaries like linear discriminant analysis does. QDA draws a little bit flexible boundaries so that it can fit the trends or the groups that your data is formed in. Sometimes or pretty often, actually, QDA also uses PCA. Remember PCA, principal component analysis, to pre-process the data so that it removes all the unnecessary what is that called, variables, and keep only the necessary information there in the data that is being trained. So sometimes QDA also uses PCA, so that's why it is kind of much more suitable for our purposes. Usually we have small data, right? We have a very varied data, so that's why these kind of low-level classifiers but flexible classifiers help us in our works. Any question before I go further? Is it okay? Yeah? Okay. So then, that we have seen that there are supervised, unsupervised. There are so many different within supervised or unsupervised itself. There are so many different types of classifiers. The question is that where do these classifiers actually differ? And they differ in terms of, as I was saying, the kind of data they handle. You might have a system which needs to check let's say the apples if they're ready to go to the market or not. It is a simple system actually. It has to make only one decision whether the color is correct or not, the shape is correct or not, and then it passes or it rejects, right? But if you think about speech, the same person who wakes up in the morning, his voice is totally different by the time he is in the afternoon. Right. So these kind of systems would need much more flexibility than the apple sorting thing. So if the classifier is better, of course it can handle more complex data in the sense of the image data, for example, image with a lot of information, right? Also a lot of noise, right? What can be complex data in case of speech? It can be a lot of people talking at the same time, with a lot of noise in the environment, right? And as you go on, you will probably also know why it is the case that better classifiers are actually better, because it knows how to handle the noise. It finally knows that noise is not something that I'm going to model. I'm going to take the noise out of the speech, and then I'm going to model only the speech. So as I said, speech is such kind of complex data which needs usually a better classifier, and that's why in this case we are basically using the QDA. So this is the idea of this is not going very well, but you can still see what is happening here. So here, let's say there are two class data. There are two classes here, the red class and the green class here, right? And the ideal way of discriminating this, or ideal boundary here, right, should be this, this dashed line. Okay. But as we train on, it was actually trained on real data. As we train on, you can see that logistic regression, which is one kind of linear regression, linear discriminant basically. You can see that it does it in the straight line, ignoring this part and this part, etc. Right? So it is missing some data, so it is never going to be correct in that, because your baseline or your original data boundary is actually should be like this. This is the ideal data boundary. Now let's look into QDA. QDA actually, see, its boundary is exactly like this. It is already flexible boundary, and it also makes it flexible based on how you populate the data, right? And that is why, as I said, it is more flexible, because it can make the spaces, right, bend, right, according to the data that comes in, right? It is, to some extent, it is flexible. And that's why we are using QDA, and I'll show you some use cases a little later. Now, what could work even better than this? What could work even better than this? Any idea? What kind of classifiers would even work better than this? Well, let's not it not be a factor. Yeah. Something like a neural network, right? A neural network. A neural network can actually deal with even more complex data. So now here the data is actually very simple data, because you can already see one group and the other group. What happens if the data is from has a completely different oblong shape? So this is what happens in the training of neural network, artificial neural network. As you can see, the classes are actually here the same class, and this is another class. And as it goes, time goes on, it can actually the ideal boundaries are given in the dashed line here, and as the time goes on, with enough data and time and processing, it can go on, match its boundaries according to the data, right? It can model it much better than the other classifiers that we have seen here, and that is why neural networks are better. So this is, I have taken it from mathformachines.com. If you are interested in some of this, this guy has an amazing website. You can have a look at it. Okay, questions at this time? Why is it called quadratic? It is basically because of the reason that it is not linear, right? Any other question here inside? Okay, so we'll stop for a minute, for 10 minutes, and then we'll be back here. Right. So as I was showing here that the artificial neural networks work the best here because it is able to deal with the complexity of the data. Sorry. Yeah. So, and then usually we know that that the speech science itself and speech technology had a quantum leap after neural networks came into being. Even though it's not a new idea, it has been an old idea. However, it could not be implemented because of the computational power we had, less computational power we had in the world. But later, post 2000, it saw a quantum leap because of not only because of the new deep neural network algorithms, but also because of the computational power that increased. So the neural networks are better for speech because their ability to capture the contextual variations in speech. So as we have already talked about that in the same sentence, I mean, speech is it's a time defined process. I mean, it just goes on for several seconds at one go, and within those several seconds itself, it changes its characteristics many times. So they also have to take care of in what phonetic context and what environmental context they are spoken. So there are quite a lot of variables which make speech variable for even one person while the person keeps on talking. It does not need to provide. You don't need to provide in the most of the cases in the neural networks. Modern neural networks, you don't need to provide any features, because as I was saying, that they can identify the features by themselves, and they can take the most important features, extract most important features, and then start modeling based on those important features only. So that there is no longer any need of handcrafted features or features such as F1 and F2 or MFCCs. If you know about MFCC features, they had they ruled the world of speech recognition for a long time. But now we no longer need them, because the network itself can decide on what it is going to hone on and how it is going to give the best performance using what kind of features. So it can get its features on its own. It's a kind of what we call the end-to-end system in that sense. So the variations in speech captured very well, because in the same speech, when I'm talking to you now, I'm changing. Juraj was talking about it also. I'm changing my intonation. My fundamental frequency goes up and down. Sometimes I'm louder, sometimes I'm softer, and with that there is a change of background information, background noise also. All that are being captured very well in the neural networks, and that's why it works very well for the speech recognition and speech-related activities. And also it is able to model complex relationships, as you say, I was talking about the contextual information, how preceding consonant changes the following vowel, etc. All these informations can be very well represented in the very well taken care of by the neural networks as such. However, the only problem is that it needs a large amount of data. We have been talking about it many a times. The point has come up again and again that neural networks, we all know, need a huge amount of data. Of course, there are ways now you can have a network trained with smaller amount of data, but still that if you want to start something from scratch, of course you need quite a good amount of data for training these neural networks. Considering that our kind of work, which is basically smaller linguistic data and using the classifiers not to actually build a system as such, not to build a speech recognition system or not to build a text-to-speech synthesis system, but we want to leverage on these technologies so that we can basically use them to, how do I say, like validate certain hypotheses that we have about the language, or we want to validate something about the structure of the language, something about its phonetics or something about its phonology, etc. In those cases, it is a good idea to have, like, a machine learning algorithm which classifies things well, but does not require at the same time bigger, large data. So we use QDA for that reason. Why to use classifiers again? In many cases, it is not possible for us to validate our hypothesis with native speakers, or like, it may be cumbersome to do certain kind of experiments also. So certain hypothesis testing can be conducted by means of this the classifiers, and I'll give you some examples of that in the second lecture also. One of the things that I have talked about in the first lecture is that the point that how Assamese vowels differ geographically. For example, from east to west, as I was showing with rhythm also, the vowel qualities also basically change. And then what we know is that there are 8 vowels in standard Assamese, but as of now, when we speak Assamese, actually these 8 vowels are reduced to smaller sets. So for example, like, as I have talked to you the other day, the O vowel is neutralized to the U vowel in speech. Actually, the U vowel is neutralized to U vowel in the Eastern Assamese. And in case of the Western Assamese variety, that the same vowel is neutralized to the O vowel. So it's some sort of neutralization process that is happening in the Assamese varieties. However, that is very difficult for us to ask to, how do I say, prove that hypothesis with people. The reason being is that many people are aware of how one should speak, right? But they don't speak in that way. However, if you ask them whether this is a correct way of speaking or not, they might give actually different answers. They might say that actually what I am speaking is not correct, and it is very common to say for people that that this is not how they actually speak normally, or they should not be speaking normally. So in those cases, we can look at how people are actually processing these kind of vowels with the help of some sort of machine learning techniques, which I'll show you in a little bit. As I have said again, I'm reiterating the point, but you probably have got it by now that the easternmost 2 towns, Tinsukia and Jorhat, they speak the eastern variety. Nagaon speaks the central variety, and Nalbari and Borpeta uses the western variety of Assamese. That is what we have come to know from literature. But has anybody provided any proof for that? No, not really. Right, so in Lina's work and our lab's work, we have been working on this, and we have been trying to see how, how correct this is, whether we can actually categorize things or classify things into 3 different groups or 5 different groups. That's what we have been seeing in different aspects of Assamese speech, sometimes in case of rhythm, sometimes in case of vowel, etc. So in case of vowel, what we have done a few years ago is that we have taken some vowel tokens from these 5 towns, which were about about 14,289 vowel tokens that were produced in both isolation in sentence frame. And then from the 5 regions, we had 72 speakers. So immediately it tells you that the number of speakers was not balanced across all the regions, which is something that Juraj was pointing out to, and I'll show you what happens when you don't have balanced data also. So in case of Assamese data that we collected, what we did is that I'm coming to the point how I'm going to use a classifier in that in a little bit, and to prove what. So the vowels are embedded in the grammatical words in Assamese in CVC kind of syllables. And these are the values that we have extracted. We have got all three formants, formant 1, formant 2 and formant 3 at the mid 20%. So if you remember some of the recent literatures, many of our linguist friends would know that we have been doing vowel measurements at the mid of the vowel. But for the last so many years, that is a little bit out of trend, and people are saying that we should always get the mid 20% of the vowel calculated, because that gives the best kind of approximation to the real production of the vowel. So we are basically doing the mid 20% of the total duration of the vowel. That is where we are getting the F1, F2 and the F3 vowels of the vowels. And also, like, we got duration of each vowel, and also F0 at the vowel midpoint. If you are worried about F0, don't worry about it, because you would have a natural tendency to come out and say that, well, that is gender dependent or person dependent, but we took care of it because we had the normalization done on the data. We used the Lobanov normalization method, which is usually also called the z-score normalization method, which was I cannot recall who talked about it first, that was the best method. Nevertheless, that's not the most important thing, but what is the this normalization method doing? Basically what it does is that it takes a vowel or any sort of speech signal, like such as F0 or any kind of spectral kind of values, and then basically deducts subtracts the speaker average from it, right, and then divides it by standard deviation of all the values. What happens is that then all the variations are also being taken care of. So if you do z-score normalization, then you, as I was showing you the other day, you get some values for vowels, not in hertz anymore, but in some values between -1 or -2 to all the way to +1 and +2, something of that sort. Right, so it is a normalization. Basically what you are doing is that you are taking the data and putting the speaker out of taking the speaker out of the data. So what we did is that here to capture because the vowels are not only they are not steady, right? We always think that the vowels are monophthongs are always steady, but they are not steady, and it has been shown in certain studies that the movement of the F1, F2 are actually important cue in vowel identification in certain languages. So what we did is that we basically took the first three density coefficients of three formant trajectories. Now, what is density coefficient? So this is exactly what I was talking about to you earlier, that how I can reduce a large information into smaller bits of information, right? So density is a method by which we take the total the vowel formant values at different points of the vowel. However, we run it through the DCT conversion algorithm, by which we can get certain coefficients, certain markers. For example, DCT coefficient number 1, DCT coefficient number 2, number 3, and you can go n number of coefficient, but we don't need that many. 2 or 3, that is what we need. We just got 3 of them, right? So these DCT coefficients, what they do is that C0, the first coefficient which we extract, C0 is nothing but the average of the total duration of the vowel formant, right? C1 is nothing but the slope, one-way slope of the total vowel formant trajectory. Basically, it is a half cosine. And then C2 is a full cosine, so it goes like this and this, right? And it compares the whole vowel trajectory with those shapes and gives a number how much it matches with the trajectories, right? This is exactly the method by which this was first used in JPG format. So that is how your large photo files become small, because they save it in these coefficients and then recreate it. And in the second talk, I'll also show you how we have actually captured with 3 coefficients. We have captured the tone, complete mesotones but again we reproduced it with just those three coefficients, just like what you do with your JPG file every day. When you are clicking on it, it just, the algorithm goes and then just like, takes the information from the minimum number of coefficients and produces a nice picture to you. So we basically took the first three DCT coefficients, right? So these are basically telling us about the form and how the form and trajectory is going up, down, or up, down, etc. So we also had like information about the speakers, the vowels, gender, context, whether it was spoken in a sentence or in isolation, what was the preceding consonant, what is the following consonant, onset and coda, etc., etc., and we just subjected it to a classifier. What is the classifier we used? We used something called the random forest classifier, and I was just mentioning a little bit earlier about this random forest classifier, which is one of my favorite classifiers because it does some sort of decision tree wise calculation of the best score it can get for a particular category. It is a little bit complex, but I have, we are in the break, I have actually a small PPT where I have shown all the branching, how it makes the decision. So I'll be happy to show you that in the break. So we use the random forest classifier. I don't want to go into go into the details of it because so basically what you know is that the number of trees, decision trees we have, the more complex decision trees we have with more number of features, the better results that we are expecting to get. And there are many of these parameters that you have to define in the random forest classification. For example, how many trees do you want? How many nodes should be in each? How many nodes should be in each tree, etc. And that we basically do, what we do is that we have in our SMEs data case, I think we ran it for 5 or 6 days together on a computer continuously until we get the best value, which is not a very smart way of doing it, but we did it that way because we did not know how to do it in a better way at that point of time. So we did it that way, and we found out what could give us the best trees, what could give us the best nodes, etc. So when we did that, when we subjected this data there, and we asked the system that okay, tell us now, if I give you unlabeled data, right, can you predict all these regions? When we gave Borpeta unlabeled data, only 22% of that data that we have, unlabeled data from Borpeta we have given, it was able to do it correctly. If you go to Jorhat, 100% of times. If you go to Nagaon, 100% of time, Nalbari 97.4% of time, Tinsukia 0, right? And all the Tinsukia data was recognized as Jorhat. Not a good classification overall. It's a failure basically, right? Can you guess why this data is read as Jorhat data? Both of them are Eastern, right? So some of these classifiers have this bad habit that if your data is not balanced, right, it is biased towards the class which has more amount of data, right? And random forest is basically infamous for that, right? There is a whole paper on the bias on this kind of what is that called? Unbalanced data biased in a random forest classification, right? So what we did is that when we subjected this data initially there, we subjected it completely unbiased, where Jorhat data was quite a lot. So as a result of that, everything was more or less going towards there. The Tinsukia data was going towards there, right? And as a result of that, Borpeta also had lower accuracy because Nalbari had more data, right? So there all these problems were happening at that time. Oopsie. I will not go to this now, but I'll show you what happened. This is when we changed the data, we made the data balanced. How did we make it balanced? There is no other way. There are two ways actually. Either you produce more data, right? People basically what they do is that they have some data augmentation method by which they increase the data. For example, you add a little bit of noise there or change certain parameters and make the classes equal. Or the best is that they will go to the lowest minimum, right, and keep everything in that. So that is what we did, and then this is what we have got. Now we are getting pretty good performance here. The average accuracy has gone up to about 94%. That is not the point. This accuracy, we are most of the times when we are doing this kind of classification, we are hung on this accuracy. But it is not the accuracy that we are interested in. We are interested in the fact that just by looking into F1, F2, F3 and duration of vowels, only vowel characteristics, we are able to get 94% classification of the dialects. That matters to us more. Even if it had been more than chance level, I would have been happy, and that has happened in as you know, I have given you several examples. In many cases we have got it only above the chance level, right? So this is working fine, but more important thing is that it is not about getting it automatically classified, but what we understand from that. What we understand from that is that in these 5 areas, the inherent properties of vowels are very much region specific, right? And that is probably why somebody who comes from Borpeta can immediately be recognized by somebody who is from Tinsukia area, right? But for me as a Tinsukia area person, a speaker, it will be very difficult for me to distinguish between the Nalbari and the Borpeta person, right? Because I know that is Western, but I don't know how to subdivide it. But from within the Borpeta area, again within the Western area, all the different groups, subgroups, they can actually distinguish each other's speech, right? But this guy is doing much better because it has information equally about all classes, right? I, as a speaker of Eastern Assam, I don't have equal data for all the areas. I have only more data. Actually, I am biased more towards the Upper Assam or Eastern Assam variety, right? I have no idea. I know that this is not us, but I don't know what are the subclasses in that, right? Because I myself is not exposed to balanced data set. So this is again actually still unbalanced data, but then we, how do I say, group them together according to Eastern, Western and Central, and then it gets a little bit better here, 94, 61 and 88, etc. But that doesn't again help us. Actually it is happening because the data is now more in each group, but still you can see immediately Central has only one place. As a result of that, the accuracy is much more lower. So in these cases, I have proved the hypothesis using the balanced data here, but one point is that I should be very careful to collect balanced database a priori, right? So what we know now is that these classifiers that we are doing using here, we are not using the classifiers actually only for the for speech recognition or TTS, etc. But what we are trying to do is that we are trying to use it for some sort of hypothesis testing, which will give us some insights into the phonetics and the phonology of the languages. What we also know is that there are many such classifiers. Some classifiers are much better, which can take care of this inherent bias of the amount of data by themselves, but some classifiers are very bad at that, right? And so they are inherently biased towards the class which has the highest amount of data. And then, as I said, the random forest classification, which we have talked about just now, it is known to be prone to errors due to the imbalanced data classes. So balanced data class, balanced data sets, they basically increase your accuracy. Okay, questions at this time? Yeah, so this is a very good question from so many, that the classification of these dialects is very much vowel specific. Has there been any study on analyzing other sound properties like consonants, stops, clusters, semivowels, etc., which can help distinguish Assamese dialects or distinguish dialects in general in research? Well, people have done different such kind of studies, but not for probably for Assamese. Assamese, we have done rhythm studies, as you have seen earlier. I cannot recall at the top of my head right now such studies, but for example, semivowels are already done in case of the English varieties, right? That is where that paper was, which talked about this, calculating the mid 20% of the vowels, where they looked into the monophthongs and the diphthongs. So there are studies on diphthongs. We have looked into Indian English diphthongs to some extent, but consonants as such to check dialect distinction, I cannot recall any. I mean, any acoustics, such kind of acoustic or machine learning based studies at this point of time. Juraj, do you have any input on that? Yeah. So Juraj also does not have any input on that. But if we come to know, if we get to remember something, then I'll surely share it. But another thing that I just wanted to mention while you asked this question is that that is why, I mean, when you do these kind of work, such as getting consonant information, vowel information, or semi-vowel information, that is dependent on the segmentation, and good segmentation. So quality of segmentation, how you have annotated the data matters a lot. And one of the reasons why we are doing it today, this particular course, is to show you that without probably taking that kind of micro level details, or that micro level details can also be captured in larger chunks of data without having to do very micro level analysis like what we have done in the past. I don't know if I made my point clear or not, but that is what I wanted to say, that that's why we are doing this course. That's so that we don't have to look into such micro details, but larger chunks of data can still capture such micro variations. That's what the point is. And I had something else which I'll probably remember later. Any other questions?
So, as someone who has no experience in machine learning whatsoever, like so theoretically things are clear. It'll be great if you can in brief explain the whole process, everything.
So what you are doing saying is that
The steps.
What is that called? Hands-on. If you can do a hands-on, that is what we are going to do. In the tutorial session. Lecture sessions are mostly for theory, and then tutorials we do hands-on.
Okay, great.
So that the files that were shared with all of you by WhatsApp, they should open automatically once you put them on your Google Drive, right? So that is something that, but anyway, yeah, let's do it in the afternoon, so let's not get confused on that. But but it's coming. It is there.
So, building on what Shomni was saying, is there a reason why most of the studies that we've looked at here are so vowel specific? Is it because there is, I mean, simply in numbers there are less vowels than there are consonants, or is it that you find, is it easier to find intonation and pitch in vowels versus consonants, or is there another
No,
reason?
I think, like, you know, as I also mentioned in the first lecture, that some things that we do are based on what we know a priori, right? That, like, you know, there will be vowel variation, but everybody talks about it, but we actually don't know what that is. So that kind of curiosity basically leads to these kind of research. And also, like, you know, if you look into individual scholars or individual, like, you know, phoneticians, then you will see that each phonetician has some sort of interest or some sort of fascination for certain 20 millisecond segment of speech, right? So unfortunately, most of the people who were working on those projects happen to be those who are interested in vowels. And one of the reasons why I also talk about vowels more is because everybody has vowels. Well, everybody has consonants too, but, like, you know, but everybody may not have tones, for example. So that is why I like to, like, give more examples from vowels. But in the second half, in the second part of the talk, I'm going to give completely tones. Yes.
This works? Yeah. Again, maybe Priyankoo sort of mentioned that earlier, but this all of the sort of phonetic detail and analysis of phonetic detail depends on how we operationalize the given question. So for the vowels, we have the straightforward or well-established way of operationalizing the differences in vowel quality in terms of formants, for example, and form and movement. In consonants, it's much more complicated, you know. But there is a huge, actually, field, one of the biggest sort of areas of research in terms of consonants and in phonetics overall, and it's a voice onset time studies, you know, because this is a very important feature in West Germanic languages, and of course, traditionally the field was dominated by the Brits and the Dutch and the Germans, where this particular thing is very, very, very dominant and very interesting to distinguish some particular things about those languages. So VOT, voice onset time, is one of the possible operationalizations of dealing with consonants. But consonants are so varied that the VOT is not necessarily relevant for many languages, for many voiced consonants, for whatever clicks, or for many other fricatives and many other types of consonants. So consonants are very difficult to study as a group and study sort of cross-linguistically. That's what Priyankoo was saying. Everybody has vowels. Vowels are quite straightforward to study cross-linguistically, but consonants are much more varied and much more. It's quite difficult to do typology on consonants, in particular if you want to do it in a quantified way. So you want to so very signal-based, because it's very difficult to operationalize them. Of course, there is a possibility that some of the things which our black box solutions actually are black box approaches actually dealing is that they capture some of the consonants. This is going to be, we are going to discuss this on Friday, because this is going to be this is the biggest task we have ahead after we finish this course, to figure out what we're actually looking at and how can we zoom into some particular questions, like looking at, I don't know, VOT for the measure if we want to replicate some work by somebody else, and consonants and consonantal dictionaries and whatever, vocabularies and all of those type of things. So yeah, consonants are tough. Vowels are easy, tones are relatively easy, but consonants are tough, and it's not very well defined area of investigating consonants, as it were.
Yeah, another thing is that, like, you know, you see, the duration of the consonants usually is very short, like, you know. Secondly, as Juraj was saying, if you think about even fricatives, there are only a few measures that you can actually take from fricatives. They are not, like, nothing has actually come up. We have celebrated 50 years of VOT, right? but like nothing has happened in case of the other sounds, for example. They are still waiting for their day.
Importantly, whatever measures you take from fricatives are completely irrelevant for some plosives, or completely irrelevant for I don't know,
Contexts, for example.
yeah, or many other types of consonants. So it's sort of very difficult to compare the realizations of consonants overall, because like it's difficult to find what you measure. And of course, even how long are consonants? It's what is the part of consonants? The full closure, the part of the consonants, the burst part of the consonant. All of those things are sort of, and they are very language dependent, potentially dialect dependent, potentially even sort of idiosyncratic in some cases. So this is difficult one.
So nasals, for example, like if you look into Styler's work on nasals, then you see that for every language the characteristics change so much that you cannot use this measurement in X language, that measurement in Y language, etc., etc. So I think very interesting questions, though.
Oh, what are you? I thought it's level 15. Yeah, that. Okay. I got it. Sorry? I saw 11:15. I clearly saw 11:15. What is it now? Okay, sorry about that. Okay, so we don't have any more knowledge at this point of time, probably. So we'll come in back. Take a break, come up with something. Yeah, what time is the next one? 12? 12. Oh, yeah. No, for us, I thought that some people actually I gave that demonstration to Juraj to go to Finland.
can we generate this in terms of the vowels? So can we specify those in a sense that can I look at the language differences simply based on the vowels and separate it from the dialectal difference in the lingua franca? So, or is it going to read it in the same way? But definitely their own language is going to influence the way they speak Mizo, right? So, do I run it differently or?
See, when they speak Mizo, you already said,
Mm.
sounds like Southern.
Yes, yes, yes.
Actually, there is something in it.
It's in the intonation, right?
Or maybe we think that it is intonation. Sometimes it might be only one sound. Right? Or sometimes only some vowels. Who knows?
So I won't have to run it different in a different separately.
Yeah, history. If you, like, for what purpose? What is your purpose?
If I'm going to look at the dialectal differences in terms of say I want to look at I want to study all the languages of Mizoram. So if I look at these
Okay, we can come to the lecture number 6 now. The use of classifiers for addressing research questions in prosodic typology. Oops, I'm not changing it here, I'm changing it here. Yeah. Okay, so the kind of prosody that we are going to talk about is a kind of a very short-term prosody here, which is going to be tones. So I'll be talking about the mesotones again, and a few features that I want to discuss with you, including the ones that we have talked about a little bit earlier about the C1, C2 of the DCT and how we have used in, or how one can use those kind of features in the analysis of tones in the tone languages. Then I'm going to let you know a little bit about the classification efforts that were done in the mesotones, and we have seen that some of the works have recently come up on several northeastern languages on classification of tones. We are doing also classification of Angami tones, which I mentioned to you yesterday is not a very easy task, considering that it is only level tones. But meso was a very interesting case. I mean, it is a very interesting language altogether. And then finally, I'm going to talk about some work that we have done on mesotone Sandhi, which has some bit of validation from machine learning. So this is essentially going to be a very short, like one slide information, but the context is very interesting, and then how we have looked into the machine learning, what the machine learning algorithms has given us, and what we have come to know about how people process tones is kind of interesting. So this is what we are going to do in the next maybe 55 minutes or 45 minutes. So if you remember, I mentioned to you the other day that there are 4 tones in meso: the high tone, falling tone, low, and rising tone, as far as we know. I mean, as far what we have confirmed so far. And then what happens in case of meso is that high tone is the only tone which is static, which is which remains almost like level like this, and all the other 3 tones are dynamic in nature. And then in terms of linguistics, these kind of static tones are usually called registrar tones, and those dynamic tones are called contour tones. And then usually it is common to have languages which have a combination of both contour and level tones. But some languages are very less number of languages which have only actually level tones. Yoruba is a great example of a language with only 3 different level tones. And then again we have Angami, which is probably one of the highest tones with one of the highest number of level tones, which is 4, or according to some earlier descriptions, 5. So if I'll try to play this. Can we increase the volume a little bit, please? Can we increase the volume a little? What is happening? Aha. So I think it's it's not connected probably, right? It's playing from the CPU. No, it's coming from the CPU. It's not connected here. Maybe from there you have to change the output to that. But it has it there. But anyway, I may try to attempt, and then like I have meso speakers here who will correct me, like if it is thang, right? Thang, which is like falling, and then thang, thang, which is the last one is the rising. Did I do it reasonably okay? Yeah, thank you. Yeah. So for those who are online, she said I did very well. So, so as you can see, like these are the 4 mesotones. The first one, as I mentioned, was the only one which is high and static. The others are, as I said, falling, rising, and even the low tone in meso is not exactly it's a level. It's not a level tone. It actually has a little bit of falling contour, and that causes another problem that I will show you a little later, probably in the slide. So if what we have done is that we have actually, over the years, we have collected quite a lot of meso data. So at this point of time, for these kind of representations, we have about 50,000 tokens, around 49,000 something number of tokens for the 4 mesotones. So when we get all that data, average them, and then we normalize them by the method that I have already mentioned to you earlier. So this is what we get. This is on the normalized scale. So you have it from -1 to 0.8. So it can go up to like whatever. So if you look into this, this is what the contour of the high tone looks like from 50,000 tokens. This is what the contour of the falling tone looks like. This is what the contour of the low tone looks like. As you can see, there is a like a slant here, and this is what a beautiful rising tone in meso looks like. I mean, there cannot be a like more prototypical rising tone than probably this. So you can see like that these are the characteristics of meso. So now our question is that like what do meso speakers actually listen to when they are trying to identify these tones? There are several studies on these kind of issues actually. If you look into some 20 years ago, there were some studies which said that Chinese kind of languages, which are also like contour tone languages, the speakers are able to predict the tone much earlier than the level tone languages, because they, by the slope of it, they already know where it is going. So what we did is that we basically tried to get these different slopes. As you can see, this is level, but this is falling, and this is rising, etc. This is a little bit falling. So what we tried to do is that we tried to use the DCT method that I have mentioned to you earlier, the discrete cosine transform. And then what we tried to do is basically, which is a formula like this. You don't have to worry about this, but it is easy to write it on a Pratt script, so that you can just write this script and convert all your tone data into the DCT coefficients. So essentially what is happening here is that in the total life of one particular tone, we are actually getting the F0 information from different points. Usually in case of meso, we have been taking the F0 values at every 2% of the total duration of the tone. So what we do is that we measure the total duration, the length of the tone or duration of the tone, and then we try to get it at every 2%. We tell our script to get the F0 value, and that is how we have been doing for several years now. So essentially you get 51 points of data for each tone, right? And from these 51 points of data, what we could do is that we could basically, because now we have the data points, we can actually create some sort of coefficients for the slopes of the mesotones using this particular discrete cosine transform, the formula for discrete cosine transform. So now there are quite a few formulas for discrete cosine transform, but this is the one of the first ones. I forgot what it is called, but it is one of the basic ones. So basically you get one C or one coefficient by looking at each point. Maybe one sec, I'll just put you here. So the N is the total data points. In our case, it is total data points is 51. And then N, small n, is the nth data point. For example, in 0.0, what is the F0 value. then xn is the f0 value, sorry, n is the nth point, data point. So the 0, 1, 2, 3, 4 goes up to 51. xn is the f0 value at the nth point, and k is the coefficient number. For example, as I told you, we are getting coefficient number 0, 1, and 2. So if we plot, put 0 here, basically what we get is the average tone, average f0. So we are not we are not going to put it there. We are just going to ask that, okay, give us the average f0. So it gives us the average f0. But C1 and C2, right? If you remember what I have told you about C1 and C2, C1 we are trying to see how much is the one-way slope is going, right? Half cosine. And C2 we are trying to see how much is the full cosine, how much the signal basically resembles a full cosine. So if you have these, then basically we are collecting data at all these points. This is not 51 because I could not draw 51 of them, but you get the idea what I am saying. So basically these are points at every duration of every point of the fundamental frequency that we are collecting the data from. As I said, C0 is basically the average f0, average fundamental frequency of that whole tone sequence. C1 is basically, it's a comparison of the pitch contour to a falling half cycle of cosine curve, so which falls somewhat like this, and provides some sort of similarity measurement in positive or negative. So if the tone is also falling, then you will have a high C1 number. If it is the tone is actually rising, then you will have a negative value because it does not match with the cosine anymore, half cosine anymore. C2 compares the given f0 contour with one full cycle of the cosine curve and the presence of peak or valley in the f0 contour. So the C2 will be positive for a falling rising f0 contour and will be negative for a rising falling f0 contour. We thought that we are the first people who are using this, but then we found a very old paper from I forgot, maybe 1990s or sometime, when many of you are not born probably, and from that time somebody has already used it for fundamental frequencies in case of fundamental frequency. And later one of the reviewers actually asked us that what is the point of doing that, and we had to give the justification that it basically compresses the data. It provides some 2 or 3 values which tell us how the whole cosine looks like. Now you can see that rather than getting all the 51 values to plot it in a very how do I say, in a very detailed manner, we can just have 3 values, C0, C1 and C2, right? And then we can basically get the characteristics of the whole tone contour. You can do the same with the F1, F2 and anything that you like, intensity or whatever. So in this case, the study that I want to mention to you about the mesotone classification, we have taken data from 10 meso native speakers with 5 male and 5 female balanced. 16 unique words produced in 3 different contexts and 3 iterations. If 3 different contexts is that usually we give the first a sentence which is a natural sentence, which will tell you give you the context. For example, I'm sitting on the chair, and let chair be the target word there, and then we ask the person to repeat chair, and then finally the person says that I said chair to you or something of that sort. So these are the isolations: semantic, which is natural sentence, and sentence frame, which I said that which we keep the same one, I said something to you. So the reason why we start with the semantic or the natural sentence with the meaning which tells that I sat on the chair or something of that sort is that in tone languages it is easy to retrieve the information, tonal information, if we give the context to the person. Otherwise the person might be wondering which tones should I produce it with, and most of the times people don't get it right. Even if they do know it, if you ask them to produce in isolation, they get it wrong, right? It has happened to us even in meso, that when we asked people to produce in isolation, we got actually wrong iterations. So when you prime them with the semantic context, so they already know that, like, oh, they're talking about the chair word. So then they would, like, get the correct tone and produce it correctly. And then I asked them, okay, now you produce the target word in isolation and then produce it in a sentence frame. And in all these cases, hopefully you'll get the correct tone. This is a little bit challenging. This is why the collecting data with tone languages is a little bit challenging, because, like, you cannot do a remote mode in many cases. For example, like, in IIT Guwahati for a long time, we have collected Assamese data, and we basically gave people a list of words written and then asked them to repeat the words over phone to our server at IIT Guwahati. Assamese is not a tone language, so it doesn't matter what they say. But Mizo is a tone language, so in many cases when we collected data, we had to give people the English translation along with the Mizo orthography, so that they produce the tones correctly. In fact, with one of the ASR systems, speech recognition systems that we have built here, which is for agriculture products, I think it is one of the probably very high, with very high accuracy, I mean, compared to, like, other low resource languages. And we have several works on it, so if you are interested, you can go and look into those. So out of these 10 speakers, I think we should have had in total 1,400, and there were some were discarded because of, like, mispronunciations, etc. So 1,384 tokens were basically what we collected at this point of time for this particular study. And then if you look into the values, so now what we did is that basically we, rather than talking about average or standard deviation of the F0, we are now producing, like, all our data, all our features of mesotones in C1, C2 values. C0 is somewhere there, but because it is, like, an already average, so we are not much worried about it. My point is that now you can see immediately what is the point, what is the problem with a language like Mizo getting average fundamental frequency. The reason being is that the falling tone is like this, falling tone is like this, yeah, rising tone is like this, and if you average them, they are going to have basically the same value, right? That is exactly what we don't want to do. One of the easiest way, what we used to do earlier, is to do what I used to do earlier, is that, like, subtract the end point from the initial point and the difference in plus or minus, right? That is one way of quantifying it. But then when I got like the idea of having DCT, now you can have actually the whole contours like characteristics represented using 2 or 3 features. So that's why we started to use this DCT features of C1 and C2 and C0 to some extent. So this is, like, reported in one of the works that I'm supposed to be sending the revision day after tomorrow. And this is what happens actually, like, after we got all the C0, C1 and C2, then what we did is that we actually put back on the same algorithm, right? We just reversed it. And we tried to see what happens, do we get the tones or not? And see, look at this, these are perfect, like, the mesotones that we are getting. So that means the algorithm catches with only 3 values, right? It is catching the tone of the meso, it is catching the values of the mesotones, characteristics of the mesotones very well, right? So what we basically did is that we took all those values, put it in the reverse, reverse engineered it, and then multiplied with an average F0 for male and female speakers. So this is what we get. That also tells us that this representation is basically faithful to the original characteristics of the tones. So then we tried to, like, use a classifier to see how they bear on. I mean, this is good enough for us to claim that, like, the C1, C2 and the C0 for that matter, they capture the mesotones very well. But we wanted to see, like, actually, like, what is happening in the whole process what is getting which feature is more important, which feature probably the speakers are using, etc. So what we did is that we put the whole this mesotone thing into a quadratic discriminant analysis, just what we have talked about earlier, and the results were in percentage, and these are percentage in accuracy, in the sense how much of it got correct. So when we give only one feature, for example, only C0, which is the average pitch, right, which many of us do in case of analyzing tone languages, then we get these kind of small very minuscule values here, 32.73, 27 and 26.64. Now one important thing that you can notice here is that as things get more complicated, remember we talked about the speech being complicated, complex system. Now it is tones being embedded in sentences, and the accuracies are immediately getting lower and lower. This is the sentence context, this is the semantic context. So the sentence context is the same frame, so it is still doing better, but the semantic context is again lower. May not follow always the trend, but that is what we more or less see. Look at C1. Remember what C1 does? Right? C1 does one-way slope, right? Right? You just use C1 and you immediately get 79 point, almost 80% accuracy in the recognition of the tones, right? How do you get these values? Basically, we subject it to when we subject it to the program with QDA, then it spits out all these values. How it does is, it's a different story for another day, but at this point of time, what we need to understand is that when you train the data initially with all the labels, and then you test one set which is not labeled, then you get these accuracies as you see here. Interestingly, in the sentence context now, the accuracy is slightly higher, right? In the semantic context, which is kind of free sentence, it's still lower, right? C2 does not work as well as C1 does. So then we try different combinations, what the machine learning people usually do, they keep on adding this with that, all the permutation combinations they try, and if there is a 0.5% increase, voila, that is our the best match. So that is what we did, but the best match that we get here is in G with only using C0, C1 and C2. Remember, now I just want you to understand this point here, that rather than computing all those 52 points, 51 points, right, rather than taking the whole data, we are just taking 3 values from the each tone, and that is actually giving us this kind of good performance. This is basically characterizing the mesotones here. So C1, C0, C1, C2, including average, it goes up to 88, and if I add duration also, right, then it goes further up. You might ask me the question that what does duration have to do with it, right? And one of the discussions that we and I had the other day, we were talking about this meso being meso having a very a long vowel and a short vowel, but there is a pattern in the long vowel and the short vowel in meso. The long vowels are usually in the contour tones, right? So the machine learns that if there is a long vowel, it probably has to choose between only 2 classes, right, most of the times, right? And that is why when you add duration, it gives basically kind of better results than the other combinations. So we did another study on the same, as I told you that the classifier here was QDA, earlier one. But for Wendy's dissertation, we actually used the random forest classifier because there was no other reason, but many of us love random forest classifier. So it was a question from one of the examiner, why did you only choose like, you know, the only random forest classifier? And we had to say that because we like it, right? And then the classifier is random forest in this case. And then this case, like, you know, compared to the other case, actually we got a slightly lower score here. We got about 79.7%. Now you remember, like, you know, that QDA is, why QDA is better for smaller amount of data. Like only 1384 tokens here, right? Oh, sorry, this one was much more higher token, but still, like, you know, the random forest did not do as good as, like, you know, as the other ones did. Also, another problem is that this particular database that we used here was actually the 49,000 tokens database. That was not only for these 3 sentences, there were many other types of sentences also. Probably all those things, like, you know, together had too many variables and then gave us much more lower accuracy in the correct tone identification. So overall accuracy in this case, when we used the random forest classifier, we get about, like, you know, 80% of accuracy, let's say. So which is still pretty good for us. But then something interesting comes out with the random forest classifier. This is called the variable importance plot. As I said earlier, that many of these classifiers, many of these algorithms which are used in classifiers, they basically internally they keep on computing which variable out of C0, C1, C2, duration, etc., which one is more important. And then you include, if it is very important, then it will use that one. If there is a less important variable, then they will, like, you know, remove that one. So that is how they go about it. So it produces a variable importance plot, and the variable importance plot looks like this. So the importance is basically, like, you know, like how it is calculated is a little bit complex. Basically, you want to see, removing each of these, how much will be the change in accuracy. Now what we know is that if you look into the C1, C1 is way up here, right? And the next one is C0, next one is C2. So C2 basically does not have much to do, even though duration C2, C0, C1, all of them actually have some like, you know, role to play in the classification of the mesotones correctly. However, look at the role of the C1. Now you probably know, because the tones are like this, right? And the low tone, even the low tone is a little bit like this, right? And there is no tone like goes like this, so C2 has nothing to do much actually. Only C1 can take care of the whole classification of this one, of the mesotones. So the next thing that we wanted to, like, you know, investigate in meso is that there is an interesting phenomena that we have noticed. First, we noticed in our data, but then when we went onto the literature, we saw that it has been, like, you know, actually noticed by several people earlier, which is that, like, you know, if you have an R tone, a rising tone in meso, it becomes a low tone when it is followed by a high tone or a falling tone. So if the next tone is beginning in a higher register, like, you know, higher frequency, then the preceding tone, which is a rising tone, goes like that, that will become low tone, right? So then, it is, like, you know, in most of the earlier works, Wiedert's work, Wiedert has a extremely complex and extremely detailed work on meso. I cannot recall the name now, but anyways, Tsangte, of course, has worked on meso syntax. Then, like, you know, again, our Lalrindiki has worked on mesotones extensively. So, at least in Tsangte and then in Wiedert's work, this gets mentioned. Wiedert mentions is probably in a different way, but they mention about this, that, like, you know, when R tone is, like, you know, R tone is followed by a high tone or a falling tone, then it becomes a low tone. So something does not look right when you look into the Sandhit tone, because it sounds like too much of a phonological process that, like, you know, even if you look into the Chinese case also, like, you know, very well-known Chinese case that when you have a third tone followed by a third tone, right, the first third tone becomes a rising tone, right. So 3-3 becomes 2-3. That is what the Chinese tone sandhi rule is. In fact, like, one of the first languages where this whole idea of tone sandhi came from, became popular at least, was the Chinese like third tone sandhi phenomena. So when we look into the literature, when we saw that, like, that this Chinese tone sandhi, the resulting rising tone itself is not exactly a, like the prototypical rising tone. So it may be, like, perceived very differently by the native speakers of Chinese, and so that is what we wanted to investigate. We wanted to see how native speakers of Mizo, did I say Chinese before? Sorry, so I meant Mizo. So we wanted to see how native speakers of Mizo basically perceive this sandhi tone. So do they have a difference between L tone and the sandhid L tone, or they are the same for them? Right? It's an easy test to do. So, but our hypothesis is that the low tone derived from tone sandhi and the phonological low tone in Mizo are basically different. And what we also hypothesized is that the native speakers of Mizo can probably perceive the difference between the two. And if such is the case, our classifiers should also be able to classify the L tone, the low tone, separately from the sandhit tone, and this is what we wanted to find out in our work. So we did a production experiment first. We got some meaningful trisyllables in Mizo, and then which looked somewhat like this, not in a very good, like, not aligned very well because of some reason. So you can see that RHH, LHH, FRF, and LLF. And in all these cases, like, in many of these cases, when you have the R here, this R should be, like, basically become an L, because, like, it says that the tone sandhi basically rule says that, like, the rising tone becomes a low tone in Mizo. Similarly, like this one also, like this R tone also should become a low tone, because, like, the following one is an F tone which starts at a high falling tone which starts at a high fundamental frequency, etc. Now my question is that if this has become an L because of tone sandhi, does this one and this one, they are perceived same or different? So we recorded people speaking these particular tone sequences, and then we had quite a lot of data for that. Of course, L tone we have quite a lot of data. Right tone sandhi we had the less number of data. So, but nevertheless we went ahead with this. So there are 19 native speakers of Mizo, 10 male, 9 female, fluent in Mizo and could understand English, were participating in the production test. And then I would not go into these details. This is the standard procedures that we all have recorded in a good place and then with good recording equipments, etc. And I will just straight away go to the results here. So this is the low tone, as I was talking about earlier, it's a little bit falling. And your rising tone sandhi basically looks a little bit like this. Right, so the low tone, which is supposed to be a low tone, is actually not quite low tone. It becomes it keeps on there without falling into this like the phonological low tone. So what we saw here is in the production experiment is that this phonological, the low tone is phonetically distinct a little bit from the canonical low tone. And the sandhit tone with the resulting tone does not have any similarity to the original tone. But the question is that do Mizo speakers actually hear the differences? So for which what we did is that we took some some recordings of Mizo and with the tone sandhi case and with some of the cases where it is actually low tone because of tone sandhi. such as the SH here, right? These are SH, this means like sandhit low tone, and these are the real low tones. They are like, real low tones. And so we gave people like, an option. For example, this one was probably, I don't remember, was it lay? Maybe? Yeah. So, and they had to choose between bridge, soil, but there is another meaning, tongue also. So, but these two were the low ones, right? Either sandhit or like originally. So we asked people like, would you go for bridge or soil? One of the two options, as you can see here, bridge and soil. Bridge is going to be LH, the original L and H. Soil would be the SL, low because it is sandhit, and H. And then like, we also gave the option that if you hear both, then just tell us it's both. So I would not go into detail into this. I'll go directly into the results. So what did people do is that like, the rate of correctly identifying the two tones, right, as separate tones was somewhat like this. This much were like actually like, wrongly. So these are all the categories. This is the original L followed by H, correctly identified, say almost 60%. When it is sandhit tone, again correctly identified like, only as the sandhit tone. That means like, they gave only unary or like, one-way answer to it. When it is LF, it is 64%. When it is SF sandhit tone again, but it is again they are hearing the sandhit tone very distinctly, so it is 72%. Right, and there were some like, both, which we have not included there. So what you can see here is that like, the people can hear the sandhi and the sandhi tone and the low tone very distinctly from each other. So what we have seen, what we understand is that probably the difference that we saw in the production test of the two tone contours being totally different in terms of sandhit tone and the low tone is probably phonologized by the meso speakers, and then that's why they are able to like, distinguish between the two tones very clearly. Then we went into our like, tone classification. There was one study, there was one random forest study also, which I will not go into, which had much better results than this. But this one was our latest one, where we have used 1D CNN model, which was trained in meso tone recognition. In this case, what we have done is that we have basically like given some acoustic prosodic features, just like F0, delta F0, delta F0, etc. And then about 14,000 tokens of meso were labeled data, like were labeled tones for like including the tone sandhi was also labeled, and they were used for training, and 6,437 were used for testing. Like they were the unlabeled data. So we asked the system that okay, you make a model with this 15,000 tokens, and then spit out a model, and we'll test this 6,500 almost tokens in them and see whether it is able to distinguish the tones, like two types of tones or not. So there were about so this was all like balanced. So we had about 3,000 tokens. One class, the sandhit tone, had actually less, about 2,900, but it would not make such a big difference, and that is the reason why you have 14,983. If you do the math, then you will come to know where it went wrong. Anyway, so this is the result that we get. These are in like the ratios. So you can see that like when you see 79 here, you know that this is basically 79%. So high tone was the best recognized with about 79% accuracy, and sometimes high tone was also like misrecognized as falling tone, as we can see in the confusion matrix here. Then the low tone had the worst. If you look into that, low tone was recognized 50% of the times, but most of the times it got misrecognized as the falling tone or the tone sandhit tone. But that is the machine, and then 50% still is not very bad considering the number of classes that you have here, Rising tone, it is a very distinct, like, going up to 71%. Falling tone itself is actually, like, about 71%. And if you look into this, the biggest confusion that falling tone has is with the low tone. And now you will know the reason why. Because if you remember the first graph that I showed you, both of them, they fall like this. Finally, going to the tone sandhi, you can see that 65% of the times it is correct, almost like, matching the human judgment there. Remember, the human judgment was like, 64, 60 something, and then 72 finally. So it is matching almost the human judgment. The amount of accuracy that you have in the human perception is almost the same accuracy that you have in this particular judgment. So overall, like, we have an accuracy of 68% in the tone recognition, but that is not our purpose to do this. Our purpose was to see what is the accuracy of the low tone and what is the accuracy of the sandhi tone. So the low tone is about 50% accuracy. Okay. Tone sandhi was about 65%, and we were happy with these results. So this brings us to the point that the hypothesis that we had earlier, that the two tones would be phonologically probably different, for at least perceptually different for the mesotones, that these two tones are perceptually different also for the machine. So as I said, like, low tone has the highest confusion with the tone sandhi tone. That is also understandable, like, considering the amount of data and the various places that data came from. It makes sense that, like, it will have that much of confusion. So what did we get here? We get here that, like, machine learning classifiers can be used to capture this prosodic information, right? The tonal prosodic information are captured very well by these classifiers, provided that we are feeding them, like, enough like right data. But in many cases, like, when you have unsupervised kind of methods, then these features are also need to be handcrafted, like what we have given as handcrafted feature that is not needed there. In this case, we have used to test our hypothesis about the phonetic correlates of mesotones. So firstly, like, we saw that the C1, we tried to find out which is the most important, most crucial cue in recognizing mesotones. And we assume that a human speaker of meso would also probably listen to that change in the, like, that one-way change in the diagonal change in the tone contour in order to recognize the mesotones. And that there is almost no other way for us to, like, we can create, like, how do I say, like, synthesized stimuli to test that. But again, the limitations of the synthesized stimuli. Synthesized stimuli are most of the times don't work because people can recognize that they're basically synthesized stimuli. So we have also used them for testing the machine learning algorithm, or the classifiers, basically, to test the phonetic characteristics of the sandhi tones in meso. So this is all I have for now, and this one was about the using of classifiers to address some sort of prosodic questions. So I gave you some prosodic questions that we had here, namely, what are the phonetic correlates of tones in meso? Secondly, if you have a sandhi tone in meso, would the sandhi tone actually be in the same phonological category as one of the existing tones, or it will create its own category? And then we go for the second conclusion, second option here, and which we have also seen in several other languages which have tone sandhi, that people are actually able to recognize the sandhid tone because of its phonetic characteristics. So I'll stop here and then let you ask questions at this time. Okay. Shomini has a question which I will come to a little later. Any question there? Yes. So we have complaints from people that they cannot hear the participants asking questions. Is it working? Yeah.
Yeah. Okay. So first of all, thank you so much, sir, for it was really insightful on how different models were working. So I had one question. First of all, did you use PCA while using the classifiers? Because does it make any difference if we use that in DIN?
Here, the features that we are using are very limited number of features, anyways.
So it won't make much.
So I don't think it would. Juraj, any input in that? 2 or 3 features.
Yes, exactly as Priyankoo is saying, like if you have several kind of well-controlled features, as these kind of interpretable features, maybe the PCA, and you only have 2 or 3, there is not really... So maybe that PCA transformation should not really help the classifier in general, or is not guaranteed to help the classifier in general. So the PCA might be more useful to, as Priyankoo is saying, to sort of, change the dimensionality, lower the dimensionality of the data. But if you have 2 or 3 features only, then that probably would be counterproductive.
Okay. So, because once I used on a really, really small data set, and just for one speaker, it affected really well. RMSE score reduced to half. Yeah, and again, does changing the testing data to training data ratio affect? And how do we find what's the perfect ratio?
So I think basically people go for a round robin fashion and try to get all the training data tested in in rotation, right? So basically if you do 2020, 2080, 2080, 2080, 2085 times with 5 exclusive sets of data, then you have taken care of at least the data that you have.
Okay.
Right, so that is usually the method that people use. So is there in the literature we always see 2080. Everywhere the default options are usually 2080.
Yeah.
I have seen 75-25 too, but nothing more or less than that, probably 2080 and 25-75.
Okay, sir.
Yeah, so that if anybody else is wondering what this question was about, it was about because we talked about training data and testing data, labeled data, unlabeled data. So here in this case, we are using the unlabeled data not to achieve anything else, but to make our hypothesis correct that our classifier is working well. So her question was that how much should we test? How much data should we put for testing? And my answer is that usually we see in the literature that the training data is 80% of the data, whatever you have, let's say data that you have, 80% of the data you commit for training, and 20% of the data you keep separate and you test with that if the output is correct or not, right? And in the best case, what you do is that you do it 5 times by changing that 80% data, right, and making that 20% exclusive every time, so that each fold gets all the 5 folds get all the data, once in training, once in testing. And then again, you can average or take the best out of the 5 times that you have done. Any other questions? That clock says 1, so I'm so it's 9 minutes to 1. So any other
The clock
questions?
is still even slower today than it was 2 days ago. It seems to be losing minute a day.
Okay, so I'll go for Somini's question, which she asked at 12:41. Can the same classifier-based machine learning distinguish dialects of Moratime languages where syllables are differently, or whether analyze Moratime or stress-time language vowels? So Somini, I saw your question, and then the answer to the question, I don't have an answer to the question. Immediate answer to the question. For records purpose, I'll read it down because it is being recorded. Can the same classifier, I'm removing the SAR before, can the same classifier-based machine learning using random forest analysis be used to distinguish dialects in Mora-time languages where syllables are differently segmented? What would be a better method to analyze Mora-timed or stress-time language vowels? So, at this moment, I don't have an answer to that. The reason being is that I have to think about what are the features that basically would distinguish between a Mora-timed and stress-timed language. So far, whatever analysis that we have been doing with these machine learning algorithms are very informed kind of analysis, in the sense we already know what to look for, and depending on we are handcrafting our feature extraction method, we are getting certain features, and then we are proving our hypothesis that it works or it doesn't work, right? So as a result of that, here in your case specifically, like, when you're combining several different things, such as, like, Mora-time languages and distinguished dialects of Mora-time languages, and Mora-time versus stress-timed, etc. So I'm not sure about it. But one of the things that I can tell you right away is that this rhythm qualities, at least rhythm qualities as you have seen in our QDA work, which Lina and I did some time ago, there we have shown that these rhythm measures are, at least they distinguish some of the dialects to some extent, but I would not overstretch it to, like, to say that they are perfect in doing that. Probably, like, we have to take such classification with like such successful classification with a little bit of with a pinch of salt, probably. So we don't have any more questions, so either it has been good or bad, but I'll leave it to you, and let's break for lunch. Okay, I think everybody is ready. Almost everybody is here, I guess, so we can start. So, so now we have the tutorial time. we are doing this tutorial jointly with help from Jayashri primarily, and then from Tukka and from Abhijit. Even though I will start and Jayashri will take over some of the Python parts where she is more proficient, and then I will take care of some of the Prat parts where I am more proficient probably, and that's how we'll go. So this tutorial, our objective is to use the classifiers that we have talked about mostly today. I mean, mostly the QDA classifier is what we are going to talk about. So first of all, like first point now is to set up the Google Colab. Can we know how many of you have set up the Google Colab by now? Okay, so not many people. So maybe that is the first thing we'll do. We'll come to that in a minute. Then we'll run QDA on Assamese rhythm data. So Jayashri will do it. She will run it on Assamese rhythm data, and she will show you how to do it. And after that, we'll run a Prat script to extract the F0 mean and standard deviation from the data that you have recorded earlier. Then we'll use that sheet of data, which is like, we have extracted using Prat. Then we'll run a QDA to classify language and gender. So this is all that we are going to do in the 2 hours. Hopefully we'll be able to finish that before time. Okay, so for this part, maybe I'll just how to set up the Google Colab. There are information here. First of all, I hope all of you have the GIAN classifiers.zip, that particular file. People who are online also can start doing their tutorial here. So anybody who does not have access to this GIAN classifiers.zip file, it's not? No, you have to download it. Showing? On your laptop? Okay. Abhijit, can you just check? Anybody else has any problem with the GIAN classifiers.zip? Any problem downloading it? Everybody has got it downloaded? Yeah? Okay. So basically what we want you to do at this point of time is that you unzip the folder, and then inside that you will probably get another folder called GIAN classifier, and inside which there are some files. You don't have to even look at those files as of now. You just copy that file onto your Google Drive, your personal Google Drive. You just drag and drop it there, right? Once you have dragged and dropped it there, your Google Drive should have this particular folder, GIAN classifiers, and then these 2 or 3? 3. These 3 files should be there in the Google Colab. Google Drive, sorry. So we are online right now.
So how many of you have
Sorry. There is one more mic open. No, no.
check? Yeah, I think there is some sort of
Oh. This mic is off.
can we well, yes. Check. 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 Go to your Teams. This is for the Teams, right? So it's connected. Because I can see this. Check. Check. Check.
Check. Okay. Now it's fine. That was in the HDMI. I cut the HDMI, it was fine. So HDMI is somehow connected. Check. Again. Check, check.
Check. Check. So how is it happening? Hello?
Hello? Hello? Okay. Sorry?
I can try to mute this one, and then you try to ask the participants if they can hear you.
Okay.
Just ask the participants.
Hello? Hello? Can you hear me?
Online participants.
Online participants, can you hear me? Hello? Can you hear me? Online participants? No, that is the old one. Anyways. Okay. Now I think it's no, a little bit of. Are online participants able to hear me? Okay. Is there any problem? Like is there any echo now?
Not sorry, it's not there. I can hear you clearly.
Okay, fine. Okay, so let's get back on that. Yeah, so how many of you are done with this step now? Have you got the GIAN classifiers folder in your Google Drive at this point of time? So anybody who has not got it in the Google Drive yet? Okay. Okay, so and everybody is able to see something like that, this in your own Google Drive, right? Okay, and then it should show you should show me, right? It should not show Jayashree's picture, basically. Okay, can we go to the next part now? Okay, super. Okay, so these are the files that we have right now. The GIAN _ classifiers folder should have three different files now. The QDA rith_data.ipynb, QDA f0ipynb, GIAN prat script.prat. Okay, and now if you click on that, if you click on ipynb, one of the ipynb files, then it should take you to Google Colab, right? So can you show it in the? So you should basically get a screen like this. If you are not getting that screen now, then please raise your hand. You are not getting. So what is it saying?
Please click open with. So if you have a Google Colab option there, or just type Google Collaboratory. Is it opening for everyone? No?
Everyone is fine? Everyone is fine now? Okay, including online participants, if you have any trouble, please let us know. Okay, so then you are all able to see this kind of code here, right? How many of you know these codes already? I mean, like, how many of you already know about these codes? Like, you can read these codes and understand what is happening here. Please raise your hand. How many? Quick, you raise hands. Okay, so you can already understand what is happening, right? So for the rest, maybe Jeshri, you can take it up. What is happening here?
Yeah, so for running, so first of all, why we are using Colab is like if you need to download Python, and then there might be some version issues or something. So we are using Google Colab. So for running any Python code, we need some libraries. So the libraries used here are NumPy, Pandas, Matplotlib, Seaborn. So NumPy and Pandas are used for the mathematical calculations and manipulation of the data sets. And the Seaborn and the Matplotlib are usually used for statistical plots and visualization. So here first we have to, so since Google Colab is running in your online, so we need to mount the data first, and then we need to process the data. So for that you have already uploaded your IPN by the GIAN classifiers into your Google Drive. So first you need to read the data. For that purpose, you have to first mount your drive so that you can access your Google Drive in your Google Colab, and then you need to load your data. That is, suppose if you have a feature file like rhythmdata.csv. So this is a
Go ahead.
yeah. So this is a file where I'm going to show you this file.
Fine.
Yeah.
I'm just highlighting it so that people
Yeah.
can understand.
So you have to load this file to a data frame. Data frame is basically it is a data manipulation variable in Python. So you will load your CSV file to the data frame, and then you'll perform the later steps. So for first I'll show you the rhythmdata.csv, how it looks like.
So to show you what is happening here, what we are doing is that our old rhythm data that you have seen already, that we did QDA in one of our older papers. So that data basically we are loading here, but that is exactly not the same data, but nearby data. So we are loading it here. She will run it and show you the results, and then afterwards you will work on your own data, right?
Font size?
Or just zoom.
Is it visible? So if you can see, there are 12 columns. So for, as sir already talked about QDA classifiers, so we are now going to classify the data. What we need to do is we need to predict the class of the data based on the region. So you can see the first column, the region column. So this is our target variable, and we need to from column D to column
So
L.
these are our classes basically.
Yes,
what we
these
have
are the
talked
classes.
about.
Yes.
Yeah.
And from column D to column L, these are our rhythm features. So
So column B and C we are ignoring for the time being.
yes.
So we are just going to do it from column A as the class data,
Class data.
right? And then column D to L, as the variables that are associated with that. Okay.
So here you can see that I have assigned a particular variable name to all the columns. So we use for QDA we generally need two variables, one for the features and one for the labels. So for that, the X variable, if you can see capital X, this is the features. So here I have used as df.drop. So for X we need from column yeah.
Yeah, that sounds good. That looks good.
Yeah. So X should basically contain the commented line, if you can see this percentage V, like column D to the end up to segments per second. So I'll just read out. It's the first one is percentage V, then standard deviation of vowels, then Varco V, SDC, Varco C, NPVI V, RPVI, syllables per second, and segments per second, the rhythm features. I hope you know. So we need these features into our X variable. So this is according to my convenience. I have to include these features, I have dropped the other columns. So you can also use the previous.
So basically what she is saying is that if you look into the this X is equal to df drop here, what she is saying is that out of the 12 columns, she does not need these 3 columns as variables. So apart from these 3, whatever is there will be used to train the data, train the classes, sorry, right?
Yes.
And here in Y, you have basically the classes which is under the rhythm column, under the region column.
Region column. So we need to classify our data based on region. So we are using region in Y variable. So next, the sklearn model. This is the basic Python model for. So we are using. So for any kind of, as sir already talked, for any kind of classification, first we need to divide our data into training and testing. So here we are. There are inbuilt functions in Python which does it automatically. So I am using the train test split of the sklearn model, and I am splitting the data. So the default training testing size is 75% for training and 25% for testing, and so we are using the random state as 42. So this number does not. This number is just used so that we can reproduce the data every time, the same data. Sometimes it so happens if you don't use this random state, so every time when you run the model, you get different accuracies for your model. So if we initialize it to this default value, so you'll get the same result every time. So next we proceed to the prediction task. Based on the features using this quadratic discriminant analysis. This is also an inbuilt function in Python. So we basically fit the model into the training data, and then we make the predictions on the test data. So in the next step we find the accuracy. So the accuracy is based on the test levels and the predictions that you made while after training the data. So next step, you for visualizing the accuracy score, what is the confusion matrix? I mean, like which language is getting confused or which language is getting misclassified or classified, how we can visualize it? We can visualize it using a confusion matrix. So Python also has an inbuilt confusion matrix function which does the job, and if you don't include this but this line, so you will just get the confusion matrix in terms of the number of files that you are subjecting to the model. So now if you want the result in terms of percentage, you convert just the values to percentage using this. Next you plot the figure and then the confusion matrix. So these are the inbuilt variables that are used for visualizing the confusion matrix. So here these are some default values where this annotation true means it gives you the numbers in the confusion matrix. If you can set it to false if you don't need the numbers. So this format is, if you want, as I already said, if you want the format as only the number of files, you can use it as D, and so 0.2 is used for percentage display. And the color blue and the bars, you don't need the confusion matrix in terms of bars, so I have set it to false.
So these are two mostly cosmetic things.
Yes.
So if you don't get all of that, don't worry, because as long as it runs today, that is going to be our achievement basically, right?
So you can see a play button here. So if
as soon as you do the play button, then it might ask you for a lot of permissions, like Google will probably ask you a lot of permissions. So choose wisely and give the permissions. So that is she is only displaying now, right? So let her display, and then we'll give you the other. You'll generate your own file.
Yes. So you can see that the 5 regions, the accuracy is 37%. So you can see that. So how you read this confusion matrix is
Can
like,
you run it one more time and then show them? Yeah. And then it spits out the result, right? In case of random forest, the next time every time you run it, you're gonna get different results, because you don't know which decision tree it's going to take the average from. So
in fact, if you don't include the random states here,
yes.
So you will get every time different results.
Okay, so is this fine? So far the dry run is okay? Yeah? Is there anything? Okay. So for everybody, you are able to launch the collab, right? You're all good with that. Okay, great. So then we go to the next part. So now, did you download, have you tried downloading the audio folders from the GIAN corpus folder? No?
Yesterday you received a GIAN corpus folder. So from there, please download the audio folder in your local system. Just the folder, you just click.
If you click on the folder, then it should get the whole folder in zip form probably.
Yes, you get 3 dots. Just click and download.
And just put it on your local system. Sorry? What is Star Audio? Oh, just R audio. Okay, yeah. So no, the all audios. Whatever you have in that particular folder, yes.
Right click and download the audio folder itself.
It is the whole audio file, a whole audio folder that is there. So when you are done downloading the audio folder, you just let me know. So if it is downloaded, then you might like to unzip it, or if it is in zip format, then you want to unzip it and put it in a place from where you can access it. So after you have downloaded, and if you are already like proficient with all these steps so far, please download the GIAN pratscript.prat which is for prat, and then run the prat script. If you don't know how to run the prat script, just wait. So the prat script, you have to download it to your local folder, hopefully.
You have it in your folder, you just need to download it.
Okay, anybody is left behind? No? Okay, everybody is pretty good. You? Juraj, did you want to say something? Okay. So how many of you have finished downloading the data and the prat script? Yeah? Raise your hands. Raise your hand, and then, I mean, all hands. By downloading the prat script, I mean that you put it on your local computer. How many of you have experience running prat script? Raise your hand. Almost everybody, right? Sorry? Very long ago, but that is a binary question, so yes, still, right? Okay, so like now, if you don't know how to run prat script, after you have, can you close it and then we'll do it again? After you have downloaded the script, open your prat, right? And then don't go to open, right? Go to prat, and then here, I can actually click on this maybe, right? Oh no, that is not connected to this, right? New prat, or maybe it is, because they have a HDMI, the USB. Oh no, HDMI, okay. Okay, open prat script. And then find your, yes, the GIAN prat script. This is an automatic system now. I just speak and it automatically does all the work. So open. And then what happens is that here you can see that, like, the directory, the first directory dollar is basically where your audio files have to be located. So if your audio file, wherever you have downloaded the audio files, that directory name, that directory path that you go and paste it here. If anybody is using Windows, you might have a problem with the slashes, because in Windows usually the slashes are on the other way, right? But I'm not sure if it is still the case. Still the case, maybe. God knows. Right? So you put the directory path, and that should point to the place where you have saved your sound files. Fine? Okay? How many of you are with me until this point of time? Raise your hand. Anybody who is not with me at this time? Okay. Okay. Yeah. Fine. So what is the problem? Sorry? But no, but you are not supposed to be running it now. Wait until, yeah, open and then put your path there. So what is your problem? No, here. No, go to path again, open path. Open path script, not new path script. So you first launch Prat. Okay. Close this. Go to Prat. No, not new. Prat. Okay. Open Prat script. Okay. Now find where it is and then read it from there. Everybody has. Prat. Go to Prat on the left. Open Prat script. You find the Prat script and then. Okay. Anybody else has problem running Prat here? No? Okay.
So you're supposed to put the
Yeah, whatever the path is. I think so. I think so. Maybe. Can you show me the folder? One sec. Open it.
open this one.
Open the folder. Yes. Right click. Properties. And then copy that whole path.
Including C drive.
Everything.
Okay.
Right.
Just each individual sound or the entire folder?
No, for only the folder. It will take the individual sound on its own.
Okay. So, sir, one more thing.
Huh. So I think I need some help with the John and Rubino. Can you just go and check with the path and all? Like whoever needs help. Anybody else has any problem? No? Okay. Hello? Rishi, what CSV are you talking about? We don't need any CSV at this point of time. We are going to generate the CSV, so just wait for a few minutes. We are at Prat running stage right now. Okay? Yes, where all the you basically copy paste the path from there, right? Click on one of the files in your folder, right click and get properties and get all the whole this thing, whole path and then paste it there. Fine. Okay. So how are we doing? Anybody has problem running Prat? Or I'm going to the next step, okay? Okay. So now, here there is a line called file append. If you look into this, the next line is called file append. So basically, the directory dollar is where you are reading your data from, and file append is basically you are creating a CSV file where all your whatever you have measured using the Prat script will be written, okay? So find a place like in your desktop or some other folder and provide that path to that folder where you want to save this your file, okay? And you can, like, just for simplicity's sake, you can say that you want to create a file called pitch_results.csv, right? It's a comma separated values file, right? So every comma it will make a column basically. So the same, exactly the same file append location here, you can copy and paste on the bottom here. Another file append is there, so you do copy and paste it here. Don't change this file name, language, gender, min pitch, all these things later. Up till only pitch_results.csv, until that part only you change. Is it clear? Is there a confusion? Yes. So what I'm saying is that here, wherever you want to save your output file, because Prat will do some measurements and put the measurements in a file, right? Where do you want to put it? Let's say you want to put it in the desktop. Then if you are using, like, your Windows system, then it will be C:/ maybe what, users or something, then / your name / desktop. Wherever you want to put it, that path you put it here. Okay, who is getting it? Who is not getting it? Anybody who is not able to get it? Yeah, you can just the path, only the path you can change. Pitch results.csv you can keep it, right? And only up till here, from home to this part, you can change. So file append should be there because file append is the command. Basically, it is saying that create a file or add to a file. Sorry?
So inside the audio folder, you can create these results.
Okay. How are we doing? Are we done with this part? Yes or no? Yes. How many of you are no? No people, raise your hands. So what is the problem? Done? Okay. Anybody else has this problem? No? Okay. Fine. Can we go to the next step now? Okay. So now the next step is to run the script basically. What we are doing at this point of time is that if you have put your directory dollar correctly, you are reading your files from the directory and then you are doing some calculations and then spitting out the results here into the pitch results.csv, and you have to give this file append this location in two places, here and down here. Okay. Yes. Okay. Once you have finished that part, you can basically go here, click on run, and run the script. And immediately you will have some errors, so don't worry about it. Yes, what does it say? Oh yeah, it's fine. Show me the script. So it is because of these spaces here. Yeah, but it doesn't like it. And also, like, you have not changed it here. Right. So you can just, like, go to somewhere, maybe D drive / something, or... Okay, all good? So everybody is... Sorry? It is running? So if it is running, then there should be a file created in the location that you have put it in the file append part, which should say somewhat like this, pitch results.csv. Please double click it and see if there is anything written there or not. Okay, and until this part, until the creation of the pitch results.csv, how many people are done? Okay, we still have a few hands left, so we'll wait. No, that was Rishi's question was at 3:42. I replied to it at 3:43. Okay, running for everyone. Everybody has got it? Yes or no? Yes? No. Who are the no people? No people? Sorry? Okay. Sorry?
Yeah, it's working, but it's automatically in Excel.
That's fine. Yeah.
Okay, because I was saying something might be lost.
Mm-hmm.
It's everything.
No, it's just lying.
Okay.
Anybody is left behind? Done? All done? Okay. Okay, Somini is saying no, sir. So Somini, if there is a problem, let us know. Yes. Coming? Yeah. F problem is solved or no? Yeah? Okay. Anyone left behind? I am being shown this. Now, how do I see that? No, I think it's all good, so many. You just go and check if the file has appeared on your location or not. Yeah, in the file append location. Already admitted. Okay. So, are we all done? Anybody not done? Raise your hand. Okay. Yes, I got it. So, one of the things is that many of these scripts are sensitive to blank spaces, okay? And in many times when you have blank spaces, it also does not tell you anything. It just keeps quiet and does not do what it's supposed to be doing, but shows that it has done what it's supposed to be doing. So, when you have a folder name, don't put a blank space, such as don't put as my blank space name. If you need to separate it, put an underscore. Don't even put a minus sign, because sometimes that also causes a problem. I mean the dash, basically. Shomini, are you able to find the file now? Can you check Shomini's? Yeah, basically your file path to the data file is wrong. So it's going there but not finding any files there. That's the reason why. So you send a can you ask her to send a screenshot of the folder where her files are, sound files are, and also a screenshot of her code. Or she must not have changed the last line, the file append in the second file append. Check. How are we on that? Done?
Well, almost.
Ah.
They kind of copied the header line completely. shortly, so they have a header repeated many times. We might be actually instructive. Let's people open the CSMs, because some people have them looking very different.
Look,
That should be fine because it will, I can only write it back.
so I think we are just waiting for one online participant probably, right? And rest, we are all good. If anybody is not yet solving it, please raise your hand. Okay, so we can go to the next step. So Somini, how is Somini doing? Uh-huh. It all looks fine, Somini, but then can you just check if the audio files are within that folder, or there is another folder inside that audio 2025012T10041112-001.
There is another folder.
There is another folder inside that, so I think you have to give another slash and slash audio or something. You check the third line. Okay, so we'll just quickly go over this. No, can we go over the, no, the Pratt script. So if you are done with the other things, so I just want to draw your attention to a few things in the Pratt script. So here, what is happening is that, as you know, it is going to the directory, and then it is reading actually how many files are there in the directory. So let's say you have in total 50 files, it reads like, how many files are there, and then it asks to get the number of total, file names in that folder. As you can see here, number of files is equal to get number of strings. So whenever in Pratt scripting, whenever there is a number, the variable name does not have anything following it. Whenever the variable is a string or a text, there is a dollar following the variable name. So it is just like, so number of files is equal to get number of strings. So number of strings is always going to be a number, so it does not have the dollar. So here we have a for loop. For loops are basically for running something so many times, right? So it is asking that for I file to number of files. That means do it for all the files from 1 to end of the total number of files. So what does it do? It basically gets the file name, get the strings file name, and then I'll skip this part. Then what it does is that it selects the first file that appears on your Pratt object window and says that to pitch, that convert it to a pitch object, or extract the whole pitch of that sound and put it down there. So on Pratt, if you slow down that going brrrr, if you slow it down, then you will see that there is below every sound file, there is a pitch file that is being created. So the pitch file is basically it is getting the pitch extracted from there and it is putting into like one line. Do you have a file on your this one, the Prat main window? Okay, so I'll just maybe I'll just continue with that. So, and then after we get the pitch, so it gets pitch into, let's say, first file's name is ABC, then it says that get the F0 is equal to get mean of that whole pitch of that file, and SD is equal to get standard deviation of that whole file. So we are getting two values here for each file, get the mean fundamental frequency and standard deviation of the fundamental frequency on the whole duration. No, can you go back? Okay, after that, what we are doing is that we are asking, like, what is the language of the file? Because remember, the first three letters that you have put, right? And the first three letters are basically the language name, right? So that is why it is always good to have very well formatted or like uniformly formatted file name. So I'm saying that language dollar, because now it is a text information, right? Language dollar is equal to left dollar of the file name dollar comma 3. That means, like, go to the file name and get the first three characters of the file name. That is going to be the language name. So it is getting that information. And I'm putting something funny here. I'm saying that if language dollar is not equal to English, ENG, then say other. So I'm not keeping any other, like, your all other languages, Assamese, Bengali, etc. I'm not keeping it. What I'm doing is I'm forcing it that if it is not English, you just change it to other, right? Because now first thing I want to do is a classification between other and English, right? And see if it works, right? So now we have a bunch of, so all that information, and gender dollar is equal to mid dollar of the file name 91. If you look into the file name, then you will see that the 9th letter is the one indicating gender, which is F or M or O, right? And then I'm saying that go to the 9th letter and get one character of the 9th letter. So it is going to be one single character. So it is going to get the F. As you can see, it is getting all the M and F, etc. It is getting language as other. Go down somewhere, please. And here it is English, so it is not changing it. Okay. So we have now got in the first column. Can you go back to the script, please? In the first column here, oops, see, file append. Where is it gone? Oh, okay. Yeah, file append here. If you look into the first column, we are putting the file name, right? It is coming from here. Language dollar is coming from here. Gender dollar is coming from here. F0 value is coming from here. Standard deviation is coming from here, and then I'm asking is that after that you go to the next line and repeat it for each file. So it will keep on doing it for all the files. Basically, that is what the script is doing. Okay, are we clear about it? Is there a question about it? Right? You don't need to know, but it is always good to know, because then you will be able to troubleshoot some of the, like, when the script is not running. At least you have an overall good idea about how it is working. So after we did that, now we should get, can you show the Excel file, the CSV file, please? Now we got the CSV file, right? And now we will put the CSV file that you have in your Google Drive again, because now we are going to run our classifier, the QDA classifier, on this file. Fine? Okay? Good. How is Somini doing? Done? Good. So your GIAN underscore classifiers should now have the results that you have got, the .csv file that you have got. Okay? as it is shown on screen right now. Yes, you just put it on like this, follow this. If you are done uploading it to the GIAN classifiers folder, are you done? How many of you are not yet done? Not yet done, 4, 5 people, 6 people. Okay, so how many people are not done uploading it to the GIAN_ classifiers folder now? Not done people, not done people. Okay, everybody is done. Everybody is done, right? How about the online people? Online people are done? Well, yeah, we'll see. Okay, so there is what? I think that Bibung has some problem. Are we all done? Done? Okay, super. So now you go to the, where is that? Okay, QDA F0 IPYNB, double click on it, right? And now Jayashree will take over. So for everybody, the Colab is open now. Everybody, it is open. Anybody for who is not open yet? Everybody, it's open. Great.
So here first the classification, what we are going to classify here, the features are the mean pitch and the SD pitch. So those two will come into our X. As I already said, the features will come into X, and with respect to what we are going to classify, the language, other or English.
So the class is going to be the language, and now
language.
We have reduced it to only 2 classes, other or English, right? So basically what we are trying to see is that given average F0 and standard deviation F0, will we be able to classify English versus the other languages? Okay? Okay, let's run the code. Sorry? Yeah, we have to find out why. We'll come there in a minute. So look at this. This is important now. So now it says that permit this notebook to access your Google Drive files. Of course, yes. Right, but then it wants to know, then it wants to know, do you want me to see your photos? Which is probably not a very good idea. So this is okay, right? As far as, okay. So now she has given the required permissions. Usually for me, the first permission worked. I gave only the first permission, it worked. Jayashree, when she worked on that, she had to give first permission, second permission, and fourth permission or something. So I think, I don't know why, but it varies. Maybe they already have my data, they don't need it. Okay? Everybody is done? Uh-huh.
Yes.
Yeah, you have to play it, but it is actually running the script. But yeah, it is a play looking button. Nothing plays, basically. Okay, good. Everybody is good? Does everybody have an error? Yeah? Good. So now we have this error, right? See, like, we know that there is an error. And what is the error? What is the error saying actually? So look at this value error. Y has only one sample in class F. Covariance is ill-defined. Number one. Two things you have already got. See, class, it's also talking about class. Now you already know what class is, right? Second thing it is talking about is that what is the problem? The problem is that there is a class called capital F, right? And because of which it has only one capital F data, I am not going to run this. That is what it is saying, right? So it cannot do any covariance analysis, right? So what is the problem? The problem is that in the data set, go back to the data set now. In the data set, see, we don't have a uppercase F anywhere, right? Nowhere do we have an uppercase F, right? But wait, can you go up a little, down, down. See? And look at this. This is ASM underscore PAG underscore F. Somebody has put a, uppercase F, because of which it now thinks that there are actually three classes. Uppercase F. Right. But why is it doing gender now? Okay, yeah. Got it. Right. So what we need to do? Correct it. Right? Make it to lowercase. Okay. Another problem that was pointed by you was that some ENG English data is also classified as, also labeled as other. Right? Can we go and look at it? Okay. Look at this. Why is it happening? Because of uppercase E. So this is why we have been saying that you have to be really consistent about how you put your data, your file names, right? How you put your documentation is very, very important in order to run everything correctly. Okay? So let's correct this, and then whatever this capital or uppercase E's are, there we put ENG, 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 ENG. That is all we need to do. Right? Yeah. So just put lowercase ENG because that is all we have. There are two classes only, other, OTH in lowercase and ENG in lowercase. Fine. Similarly, gender also, I think we only have two classes here, probably M and F, right? Can we save?
Yes, saved.
And then
After saving, you need to upload it again to your Google Drive.
but they could have corrected in the Google Drive anyways. Yeah. I think so. Anyway, so whatever way you do it, see, check. It will open as. Yeah, open with Google Drive or something. But anyway, we are done. Okay, once the correction is done, let's go for the next step. Basically, you have to run it again. The play button again.
it was doing gender.
Okay, the correction is done. Did you run it again? How many of you have like finished running it? How many of you how many of you have not finished running it? Not done? Okay, I'll wait. Huh. Did you re-upload it to Google Drive? Maybe your drive, this thing address is not correct. Okay, so if online people have any problem, just let us know. Whose is not working? Working. Okay, who is having problem now? What is the error?
So you can't look at the file. Like
No, one sec.
now, just look at the file and copy the path. 3 dots.
Yeah, yeah, paste it there. Check, check. Okay, everybody is good? Good? So what did we classify there? Huh? What is the average? Like, you know, what is the accuracy there? Sorry? 97%, right? And then, let me see. So you should get something like this, right? And if you look into the code, here, you can already see what is your y here. Y basically is gender. And you have two class classification, right? M and F. So it just, you know, basically trained on the F0 data and saw, like, you know, whether it can predict or not. As we know, F0 is a big predictor of, like, you know, gender. So most of the cases, majority of your cases, 97% of the times it got it correctly, right? Now, what you do is that you manipulate the code and make it run for language types. Okay? You have two language types, right? So for language, you classify and see if F0 and your SDA or F0 helps. So anybody has still trouble running codes? If any online participants have any question, please let me know. Do it. Why not? Right. Now you know how to run it, right? You have to get some sort of variables there, right? So anybody tried running language? Yeah? How was it? For language? Possible. Maybe something like, because we did not change the ENG probably or something. I don't know why is it happening? No idea. Yeah, maybe it's more consistent with, I have no idea. We have to look into it and find out. But there are I know that the system wise there are differences, so I don't know about what server. You're right. Isn't it true that sometimes system wise there are system induced variance also in the results of accuracy sometimes? I remember at some point of time I was told that we should always try running in the same configuration system so that there are no results. Sorry? Yeah, one sec.
I actually don't know much about the QDA classifiers, but I think that the training of them is a stochastic process. I might be wrong here, but in many classifiers, like neural network, it's a stochastic process, so the result might depend simply on sort of random seeding and random sort of running the random variables. I'm actually not sure whether QDA is deterministic or stochastic. We would have to ask somebody, but that might be one of the reasons. Are people getting different results?
No, I think we are different from others, and that may be just one sort of maybe one set of data that is different. I don't know.
Yeah, or maybe because we were editing the code. Okay.
Yeah.
Then who is different? Okay. Let me see.
My guess is that it's something to do with one data. How many rows are there? 152. So it takes. Sorry? No, one second. They are random. Can you go up? Jesh. Random state is same.
Yeah, that number is easier. So there might be just one data point. So it doesn't seem that the QDA is a stochastic classifier because it seems to be yielding the same result every time we run it, and there are two types of results around. So there must be the difference in a data. Among all of those editing which we did and all that, they probably have slightly different data.
So how many rows do you have, you said? How many? Sorry? 8. And we have only this many. How many do you have? You said 150 something. People have different. No. Yeah, check the file numbers in your folders, local folders.
I think it's Sarmah because she uploaded in the meantime. She uploaded Gujarati version to the Google Drive. So maybe some of you do have Gujarati version and some of you don't. So the difference might be that you have several extra lines because the data.
So after all that grand theories we had, machine, stochastic process. So people who are online who are wondering what's happening here, the results of the classification was very different from people to people. Sorry? No, but you must already have some sort of data somewhere, right? Right. So you might have some maybe grade sheets or of some class. Right. I don't know. So I think again, we are, our, well of knowledge is now, I think, again, in dry state. Right. So I think it's about 4:45, right?
Yeah.
4:40. I don't know which. Now this says 4:45. This is 4:39, and this one is 4:39, and that one is 4:50. So nevertheless, so we'll then, I think this is all we wanted to do. We will stay here for some time. I mean, up till 5 we are here, right? If you have any questions, then we can take it. But I don't think there are much questions there. So online participants, if you have anything, just let it. Okay, Chanchal has, my file is empty. Yeah, so I think if your file is empty, that means that you have not pointed it to the correct directory. Chanchal, if it is empty, that means that probably you are not directing it to the correct directory, okay? So you check it once, or on the WhatsApp, you just send us your script, picture of your script that you are running, number 1. Number 2, the folder, with the path name of the folder, picture of the folder on WhatsApp. Okay, he found the problem. Good. So I think the reason why this one is so bad and the other one is so good is clear, because basically F0 is gender dependent. However, language is, there is nothing to do with F0, right? It might have in some senses, but not at this point of time. It is all the same speakers, so you're not getting any classification here, right? Okay. So yeah, so I'm basically doing the tutorial, but I would like to really appreciate the help that I got from Abhijit, Jayashree, and Tupka in in making the tutorial. So they worked really hard until late last night. So thanks to them. And then if you have any questions, so we are still here. So come and talk to us. Thanks. So online participants, we are going to stop the streaming now. I hope everything is good. If any problem is still there, I'm waiting here, or you can just use WhatsApp to contact me. If it is fine with you, then they're asking me to cut the stream now. I assume I saw Gyandeep saying okay, and so I guess that everybody else is okay with that. Thank you so much for joining. So we'll see you later. Bye-bye.